Siz. Good morning. My name is Bovet, and before I start with the presentation, I'd like to thank the organizing committee of the conference for their kind invitation to provide this keynote lecture. Thank you. I would like to talk today about the seismic response of tunnels, lessons learned from recent successes of failure. And what you see here is a picture of the failure of the Hcm Tunnel during the Wenchuan earthquake in 2018. This is the outline of my presentation. I'm going to
Sayın katılımcılar, öğleden sonraki keynote speaker session'ını başlatıyorum. Hocamız yurt dışında bağlantıda bir sıkıntı olmasın diye sunumunu video olarak göndermiş ama canlı olarak bizi takip edecek. Sunum bittikten sonra sorularınızı sorabilirsiniz. Bir test yaptık. Ben işaret bekliyorum yukarıdan başlamak için. Tamam mıdır? Tamam, başlayalım o zaman.
Good morning. My name is Bovet, and before
Besim, önce ben bir tanıtayım hocamızı. Okay. Good afternoon, ladies and gentlemen. In this session, we will have 4 keynote speakers, and it's a pleasure to me to introduce our first keynote speaker, Professor Antonio Bovet. Before giving this stage of him, I would like to summarize his resume first. Professor Bovet is Edgar B. and Hedwig M. Olson Professor of Civil Engineering in School of Engineering of the Purdue University, where he has been teaching for 24 years. His research interests are fracture mechanics, discontinuum media, analytical and numerical models, soil structure interaction, earthquake-induced hazards, tunnels, and problem soils. Professor Antonio Bovet has BS and MS degree in honors in civil engineering from the Polytechnic University of Madrid. After that, he worked in the industry to design and construction projects related to the highway construction, foundation design, slope stability, and tunnel design. Then he received his PhD in civil engineering from Massachusetts Institute of Technology with his thesis titled Crack Propagation and Coalescence in Rock-Type Materials. He is the author or co-author more than 100 journal papers and 85 conference papers. He is the author editor of 4 books. He gave 83 invited presentations, and he has involved in 67 scientific projects related to the 1999 Düzce, 2003 Bingöl earthquakes. He is a member of the site reconnaissance team created after these earthquakes. He is a former president of the ARMA, which means American Rock Mechanics Association. Because of the COVID situation, he could not attend in person, so he recorded a video. However, he is here with us via Zoom transfer. Your questions after the presentation. Let's watch the presentation and then you can ask your questions. Thank you.
I'd like to thank the organizing committee of the conference for their kind invitation to provide this keynote lecture. Thank you. I would like to talk today about the seismic response of tunnels, lessons learned from recent successes of failure. And what you see here is a picture of the failure of the Hcm Tunnel during the Wenchuan earthquake in 2018. This is the outline of my presentation. I'm going to start briefly about the motivation and discuss how important the issue of seismic behavior of tunnels is, and then go through 3 case studies, the Daikai station, that I'm going to discuss about a learning phase, because the Daikai was, I think, the first well-documented station or underground structure that collapsed during an earthquake, and we had a great opportunity to learn from the interaction between the ground and the structure, and the load transfer between the ground and the structure during earthquake, and it can be thought of a very large laboratory test, and as I said, because we have good data and well documented. Then I'm going to talk about another failure, which is the Hcm Tunnel, and use it as a verification of some of the things that we learned and how the approach fits or is used to compare with the damage that is observed. And finally, I'm going to talk about a recently completed tunnel, the Hcm Tunnel, that connects Hong Kong with Macau, and has a very interesting tunnel, submerged tunnel, and we did some interesting tests to look at the seismic behavior of the tunnel. Regarding the motivation, the question is why we are looking at the seismic behavior of tunnels, and it's because there is the perception, or there has been the perception, perhaps before the failure of the Daikai station and others, that underground structures are safe during seismic events, and the perception came from the fact that it was because the tunnels are surrounded by the ground, they move with the ground, and because of that, there is very little or no damage associated with the tunnels. But then we go back to the literature and what has been reported in terms of behavior of tunnels during earthquakes. As far back as 1977, there is this database, collected by Dowding, and here we have a plot on peak acceleration that was collected on the surface at the center of the tunnel, and here the cases that were analyzed. So they look at 71 cases, and here there is color coded depending on the degree of damage and the type of damage and so on and so forth. The point I'm going to make is that of the 71 cases analyzed, 42 had some damage. So it's about 60 to 70% of the cases analyzed. The conclusions were a little bit simple or simplistic in the sense that they end up with two thresholds, one of 0.2 G on the surface of the tunnel, on top of the surface of the tunnel, where below this acceleration there is no damage was observed, and 0.5 G, and above this damage there was severe damage or collapse of the tunnel. This database was expanded later on by Sharma Jat. They collected a total of 192 cases. Again, you look at the number of cases where damage was reported, it's about 50% of the cases observed. They try to classify the cases and the damage depending on other characteristics. For example, I'm showing here two plots. Here is the number of cases analyzed, and here is the overburden. And as expected, the less the overburden, the closer the tunnel is to the surface, the larger the chances of the tunnel suffering some damage. Here is an attempt to classify the intensity of the damage depending on the ground where the tunnel was excavated, and the classification range from moderate and heavy to none. And as you see, the percentage of tunnels that were damaged were on soft soils, and of course these two are related because we expect soft soils close to the surface. There are other factors, and we'll talk about those in a minute. This is just a schematic of the failure of the underground space, the underground rapid transit system in Kobe during the 1995 Kobe earthquake. The ground station that collapses, the Daikai station, was built in the early 60s, but that was not the only underground structure that suffered damage. There were more than 200 columns between the Daikai station and the Kosaku Nagata station that suffered damage. There was no collapse. There was damage also in the Kosaku Nagata station. There was damage on underground shopping mall, and there were some heavy damage in tunnels excavated in rock further on for the high-speed train in Japan. This is another compilation of data specific to Taiwan after the Chichi earthquake in 1999. again, 57 cases that were analyzed, 49 from talking about, we're dealing with about 80% of the tunnels inspected that suffer either moderate to slight damage. There was one tunnel that was crossing a fault that collapsed during the earthquake, and this is a classification based on the location of the damage. As I said, this tunnel collapsed at the crossing of a fault. There was significant damage of the portals, also damage inside of the tunnels. So as one can see, we have structures that so far we are being told that about 50 to 70% of the structures that have been subjected to earthquake suffer some level of damage, including collapse of the tunnel. That certainly, if we were talking about structures above ground, that would be unacceptable. And yet, it seems that there is a disconnect between the behavior of underground structures and how we approach them. And we have to realize that there are a number of tunnels that are still out there that have not been designed for earthquake loading. And one of those that we're going to be discussing in a minute is the Daikai Station. And the Daikai Station, as I said, it was built in the early 1960s and in Japan, and it was not designed for resisting earthquake. Closer to home in Turkey, during the Düzce earthquake in 1999, the Bovet Tunnel was under construction. It was at the location that was crossing an area that was heavily faulted at Milonite. The tunnel collapsed, and that was an effect of the earthquake of 1999. Here, what you have is a picture of the tunnel that is completed now. So what I want to do, as I mentioned in the beginning of the presentation, is talk about three cases. One is the Kobe station in Kobe in Japan during the 1995 Kobe earthquake, the Longshi Tunnel that collapsed during the 2008 Wenchuan earthquake, and then the recently completed project, the Hcm Tunnel, and more specifically about the approach that we follow in the design of the joints of the segments. This is an immersed tunnel. So let's start with the Kobe station. Some of you may be familiar with that. So this is a plan view of the station, and it shows the area that was damaged. So that section of the station completely collapsed. It's about 110 meters long. There was these columns at the center of the cross section. So it was a rectangular cross section with these columns in the middle that collapsed. There was damage on the structure that was access to the station. There was damage also on the columns, because this is the cross section of the tunnel that connects the stations, and it also is a rectangular cross section with columns at the center. There was damage on these tunnels, but not collapse. So these are some pictures of the station, inside the station during the collapse, and you see some of the photographs of the columns at the center of the cross section, and you see the heavy damage at the connection of the columns with the top slab. Also, there was heavy damage at the bottom of the slab. We'll talk about that in a minute. We did quite a bit of analysis, and our interpretation was the failure of these columns was in shear. It was some sort of brittle failure. More photographs with other columns. So you see how the core of the concrete was completely crushed, the buckling of the longitudinal reinforcement, and that clearly indicates that there was not enough transverse reinforcement to absorb the deformations imposed by the earthquake, and that created or caused the failure of these columns. Some more pictures with these huge deformations, again, because the core concrete, there was not enough confinement with the transverse reinforcement, and so on and so forth. These are some pictures of the top of the station. It was on top of Road 28, and there was a 2.5 meter subsidence, and this was directly caused by the collapse of the Daikai station underneath. This is the Daikai station as it is today. And the only thing that that is part of the old station is the bottom slab. The rest is completely new. The columns, the top slab are completely new, and these columns, they have an encasing of steel to increase the ductility of the column so that any deformations imposed by the earthquake can be absorbed. And of course, now the station is designed to resist earthquakes. The original stations I mentioned was not designed, which is not uncommon. As I said, there was plenty of tunnels everywhere in the world and also in the US that are out there in service, and they are not designed for earthquake. And now the question is what we do with those. Are those vulnerable to earthquakes? They are, how we can retrofit them, and so on and so forth. So, as I mentioned, we're going to be looking at the failure of the Daikai station as a large laboratory experiment, well documented, where we were able to learn some of the load transfer mechanisms between the soil and the structure, and the compatibility of stresses and deformations between the soil and the structure. We go back to the plan view and the vertical cross-section. Again, this is the section of the station that collapsed, all the central columns. But because there were differences in the structure along the station, we divided those into three main sections. Section 1, that was the section that collapsed. Section 2 is the tunnels that communicate the Daikai station with the Shinkai-inchi and the Nagata stations. And Section 3, which is the axis of the column. And we did that because all these three sections had completely different behavior. One collapsed, the other one they did not, and they were damaged. And yet the three cross sections were subjected to the same earthquake. They were surrounded by the same soil conditions. So the question was why section 1 collapsed and there was damage in section 2 and section 3, but not collapse. So these are the cross sections. What you see here is the cross sections of the different sections. Section 1 is the one that collapsed, is a moment resisting structure, is a rectangular structure, fairly thick members between 70 and 80 centimeters in thickness, very large, 17 meters wide, 7 meters tall, and it's embedded about 5 meters below the ground surface. Section 2, which is the tunnel that connects the stations, smaller, about 9 meters of width, about 6 meters tall, and about also 5 meters below the ground, below the ground surface. Both of them, they have these columns, similar columns, slightly different reinforcement, but the idea is the same. And finally, section 3, which is the access station, much larger structure, 26 meters of width, 10 meters in height, reaching the top of the ground, and also the central column, but you see much longer columns, and then they have this intermediate slab that divides the structure in the cross section. This is the ground conditions at the site of the station. And you see that there are two types of soils. One is a Pleistocene, mostly sands and clays, and particularly this Pleistocene gravel that is fairly dense, and then soft and loose Holocene deposits, which are on top. The station, I would say the top of the station with under burden about 5 meters around here, and the station would reach a depth of about 10 meters or so. I want to point out of the location of the water table that is about 6 meters below the surface, but these borings B1, D1, and B3, they were drilled far from the station, but close to the station, which is boring B2, the water table is much lower, and the reason for that is the station acted as a drain, and because the water table was depressed, maybe this is one of the reasons why there was no liquefaction surrounding the structure, where there was extensive liquefaction elsewhere in the city. You also have here the SPT values, and for the top, I would say 10 to maybe 16 meters. We have SPT values of the order of 10 and 20. So as I said, soft soil deposits. And once you reach these Pleistocene gravels, we begin to have very large N values. And we use this layer when we talk about the numerical discretization to have the bottom of discretization impose the motions here, and these were the motions that were recorded on a station nearby where we had data of accelerations at this particular depth. What we did was finite element simulation with the station, very far boundaries to diminish, boundary effects that we were imposing the motion, impose the motion at the bottom of the discretization that corresponds to these dense Pleistocene gravels, where we had also the motions that were recorded at Port Island. This is a strong motion station that was 3 kilometers away from the station, so fairly close. We realized very early that one of the most important parameters that control the behavior of underground structures is the relative stiffness between the structure and the ground it replaces. And in this particular case, the Daikai station was considered a stiff structure because the structure were much more stiff than the ground it replaced. However, the ground, we know also that the stiffness of the ground decreases with strains, and then the relative stiffness between the structure and the ground evolves with time as with cycles of loading. So it was very important to capture these characteristics of the ground. So we developed a model that would duplicate quite well the expected behavior of the soil. So you have here is a plot of the normalized shear modulus of the soil. This is the normalized by the shear modulus divided by the small strain or G max of the soil. And also here we have a plot of the damping ratio of the soil. And this is a comparison between the model, that is the solid line, and data from experiments from SEED and Busetic. And you see that the match is fairly good, and the trends are expected that as the shear strain increases, then the shear modulus quickly decreases, and also the damping increases. At the bottom, as I mentioned, we introduced the accelerations, the actual accelerations measured at Port Island, and these were fairly large, 0.58 G in the horizontal direction and 0.16 G in the vertical direction. The results that I'm showing you are in terms of the distortion of the central column. This is the section 1 that collapsed. Section 2 is the tunnel that was damaged but not collapsed, and section 3 is the access to the station. And if you look at the displacements, and the maximum displacement that the numerical model was predicting was about 4 centimeters. That is where the column would have collapsed. The rest, it's just a theoretical result. Looking at this distortion, we computed not only the displacement, but also the axial load, the shear force, and the moment acting at the connection of the column and with the top and bottom slabs. And we did with some colleagues, with Professor Ramirez and others, we did a structural analysis looking at the capacity of this column under this demand, and indeed we found that the column with this demand would have failed in shear at this peak distortion. What was interesting is that we did the same exercise with the running tunnel, and we observed that we would have expected damage with this distortion and the loading that was predicted by the numerical model, but not collapse. And same thing with the axis of the station, a much flexible cross section. You see that these deformations of the central column are much smaller. So larger deformations of the cross section that collapse, smaller deformations, and even though it's not significant, it was sufficient to prevent the collapse of the central column, and certainly they were too small to produce failure of the access station. What is interesting is that you see is that at the end, we don't go back to zero distortion of the column. If the column would have survived, we would have a permanent deformation of the station, and this is because of the plastic deformations of the soil, particularly with the cycles of loading and unloading of the soil that would accumulate these deformations, which is captured by the model. This I think is an interesting plot. Let's see if I'm able to explain what it shows. These contour plots are computed at peak distortion of the station. This is the cross section, half the cross section of the station that collapsed, and half because it's anti-symmetric on the other side. So I'm just showing half. of the station. So this is the decay station that, as I mentioned, was much stiffer than the soil it replaced, and we have these contour plots that correspond to the ratio between the shear modulus of the soil at peak distortion of the column compared to the maximum shear modulus of the soil. This is the shear modulus of the soil at small strain. So you move away from the structure, you expect that the influence of the structure would decrease. So you would recover what we call the free field deformations, and you see that far from the structure, then the soil, the stiffness of the soil decreases. So that means that the soil deforms quite a bit. But interestingly, as we approach the station, you see that this ratio of the actual shear stiffness of the soil at peak distortion compared to the maximum shear stiffness of the soil is much larger. So that means that the soil here deforms less, and deforms less because of the presence of the structure that is stiffer. So around the structure, the soil needs to move with the structure. If the structure is very stiff, then it's going to prevent the movement of the soil. The soil is not going to deform that much, so the soil is going to remain stiffer than the soil that is going to be away from the structure, that doesn't see the influence of the structure. The opposite is true. If the station would have been much flexible than the soil it replaces, then we would have seen is that these distortions of the soil would be much larger than those of the free field, and we would see this reverse. These values of the ratio would be higher here and would be decreasing as we get closer to the station. So in a summary, very quickly, lessons learned from the failure of the decay station. The decay station failed because they was not adequately designed. There was no design for resisting earthquake. We also learned that underground structures are vulnerable to earthquakes. Certainly, underground structures are safer than above ground structures, but that doesn't mean that the ground structures are safe. So that means that we need to design underground structures to resist earthquakes, and we have to provide them with the same level of ductility that we provide to above ground structures, such that they can survive the earthquakes. We also learned that the formations strongly depend on the relative stiffness, so the problem is not a load-driven problem like the structures above ground, because the structures, the movement is imposed by the soil at their foundation, but then the structure deforms on its own. However, underground structures, they are surrounded by the soil, so there has to be some compatibility of the formations and forces between the ground and the soil. So it's a displacement-driven problem. So that means that is the relative stiffness, the parameter that controls the response on the underground structure. Interface friction, to some extent, also influences the response of the underground structure, but not as much as the relative stiffness. And one can understand that interface friction also influences, because this is how the stresses are transferred from the ground to the structure. So we have two mechanisms, right? We can transfer normal stresses, and we can transfer shear stresses. If we have a tight contact between the structure and the ground, so that means that we can transfer all the shear stresses that we want. However, the soil is heavily constrained because we have the shear. If we have, let's say, a frictionless or low friction interface, then the shear is limited. The shear that can be transmitted from the ground to the structure is limited. However, the soil is less constrained and can therefore more independently of the structure. Because of this parameter of the relative stiffness, so that means that we need to use appropriate ground models so they can capture this change in stiffness of the soil with deformation. Of course, we also need to use appropriate models for the structure. But the point I'm trying to make here is because of this relative stiffness. The second case that I want to discuss is the case of the Longship Tunnel. This tunnel has a length of about 3.7 kilometers. It's about 2 kilometers from the epicenter of the earthquake, magnitude 8 earthquake in 2018, and that created significant damage to the Longship Tunnel and failure of the Longship Tunnel, particularly in this area where the tunnel was crossing a fault about very close to the east portal. This is a vertical cross-section of the tunnel. The tunnel is excavated in rock. It's a relatively soft rock. Only soils, colluvium were found at close to the portals of the tunnel. The rest of the rocks we have here, mudstone, granodiorite, and sandstones were the rocks that were found along the tunnel. This is the fault where there was the tunnel collapse. There was widespread damage along the tunnel itself. There was damage also the portals. I'll show you some pictures. This is the cross section of the tunnel. It's a fairly large cross section area, 9.2 meters in width, about 8 meters in height. A little bit of a horseshoe cross section of the tunnel. The tunnel had two liners, a primary liner that was shotcrete and rock bolts, and a secondary liner that was reinforced concrete, and also had this bottom slab for the pavement that it was mass concrete. There was a little bit of a reinforcement on the primary liner with steel sets crossing the fault, because this was an area where the rock was heavily fractured. This is the earthquake registered at a station, the Wolong observing station, fairly close to the tunnel. So this is the horizontal acceleration east-west. This is the horizontal acceleration north-south, and this is the vertical acceleration. And you have here the magnitudes of the maximum acceleration, about 0.9 g, 0.6 g, and also 0.9 g's. So fairly large accelerations that affected the tunnel. Some pictures about the damage observed. This is stability at the east portal with some big wedges and rocks that failed because of the shaking. Damage inside of the tunnel. So this is the secondary liner with tensile cracks perpendicular to the tunnel, shear and compression that were, along the axis of the tunnel. Significant damage at the invert of the tunnel. I'll show you some pictures. As you get inside of the tunnel and closer to the fall, the damage was much intense, with quite a bit of damage pretty much along the entire cross section of the tunnel, with some tensile cracks along the crown of the tunnel. This is the slab, the bottom slab, that it was mass concrete. Fairly large tensile crack in the middle, with then the two slabs that became independent of each other. There was buckling, so there was quite a bit of heave at the bottom of the tunnel. Here's some picture with a little bit of a close-up of the heave. So you see the tensile crack in the middle with the buckling of the bottom slab. Significant damage, as I said, that you get closer to the fault. On the sides of the tunnel, the reinforcement of the secondary liner buckling, and some areas where the secondary liner completely collapsed. So this is the impermeabilization that was placed between the primary and secondary liner. Again, there is material that fell from the crown, with huge damage at the invert of the tunnel. And this is where the tunnel was crossing a fault that there was a complete collapse of the cross section of the tunnel. And you see some of the steel sets that were placed there to increase the support of the tunnel as the tunnel was crossing the fault. A little bit more pictures of the damage. So here's the discretization that was done, and I have to credit the work done by Professor Yu at Tongji University. So this is a 3D finite element method, and we impose at the bottom of this discretization the accelerations that were measured nearby at the strong motion station. And what the exercise that we did was to input first the acceleration perpendicular to the axis of the tunnel. Then we added the horizontal acceleration parallel to the axis of the tunnel. And finally, we considered 3 accelerations because we wanted to see what are the effects of considering only one acceleration versus considering all 3. In other words, what is the difference between doing a 2D analysis, which is the standard that is being done, from doing a 3D analysis? The fault was discretized, and these are the tunnels of the openings of the tunnels, with the primary liner with the shotcrete and rock bolts, and the secondary line of the two twin tunnels for the tunnel. Here are some results. There's a lot of data, and I'm not. We don't have to go through all the details, but in a nutshell, what we have here is the maximum principal stress, meaning what is the magnitude of tension, which is the minimum principal stress, which is the magnitude of the compression. This line corresponds to the failure of the secondary liner in tension, failure in compression. And here what you have is plots that correspond to imposing only the accelerations perpendicular to the tunnel axis, accelerations perpendicular and parallel, and then the three accelerations, and we are looking at different plots when we are looking at the stresses at the ground and going along the perimeter of the tunnel until this point here at the corner between the support and the bottom slab. As I said, a lot of data, but basically one thing that is important is that yes, we see some damage with only the acceleration that is perpendicular to the axis of the tunnel, let's say the 2D analysis, but what is important is that we have a significant increase in damage, meaning points that cross the threshold of damage, both in tension and compression, when we add the acceleration, the component acceleration parallel to the tunnel. And yes, there is an increase also on damage when we add the vertical acceleration, but certainly the increase from this one to that one is much smaller than the increase from that one to this one. So the inclusion of the two horizontal accelerations, it seems that is critical to capture, we think, to capture well the response of the tunnel. Same exercise done for the slab at the bottom of the tunnel, same plots on tension with time, compression, threshold of damage in tension, and you still don't see the threshold of damage in compression because it was not expected. Same trends, a little bit of damage with only the acceleration perpendicular to the axis of the tunnel, significant damage, and a little bit of increase when we consider the three. Then we look at, is a little bit of a qualitative picture that I'm showing you here, but we did it a little bit more quantitative, and we have a comparison between the expectations from the numerical model with what was observed, and we found that there was a general good agreement. So that validated a little bit our perception, our notion that what we learned from the Daikai station when is used to predict. Of course, we predicted the past, but at least provide confidence in the tools that we have. Same thing for the reinforced bottom slab, where we could see the tension at the center, and then because of the motions of the ends of the slab, then we would explain why we would have this buckling of the central. So the lessons that we learned is that not only tunnels in soil, but also tunnels in rock are vulnerable to earthquakes. Vertical motions have minor effects, but the addition of the longitudinal motions, it seemed that increased the damage that would predicted if we only were using motions perpendicular to the axis of the tunnel. So that points, this is one case that we've done, maybe other cases, but it seems that all of them are consistently pointing to the fact that seems that 3D models seems the way to go. Of course, we have limitations with the computers, memory, and so on and so forth, but it seems that we should be start looking seriously at 3D models rather than keep doing the 2D models. And it seems that the tools that we have are sufficient to predict the damage that was expected. Very quickly, looking at the Hcm tunnel, this is a very large project that has recently been completed. It's an infrastructure that connects Hong Kong with Macau. It has two very large structures, a bridge that is about 23 kilometers long and an immersed tunnel that is 6.7 kilometers long. And this is what we are going to be talking in a minute. So you have here a sketch of the tunnel itself. And this is the cross section, very large elements, 38 meters wide, about 10 meters tall, is composed of 33 segments, each one 180 meters long, and as I mentioned, 38 meters wide, 11 meters high, and each one of those weighs 76,000 tons that are built outside. They are floated to the place and of installation. They are submerged, and then they are they are tensioned such that with a joint, and that's going to be the point of focusing on discussion. And this joint, as the edge segment is compressed, provides the water tightness of the tunnel. This is the area of interest. As you see, the tunnel is in fairly soft soils, with the bedrock a little bit further from the bottom of the tunnel. And this tunnel was analyzed in an exceptional facility that Tongji University has in Shanghai, where they have 4 shaking tables that are independent of each other, that are installed on a 70-meter long trench. Each table has dimensions of 4 meters by 6 meters, it has a capacity of 70 tons, and can produce an acceleration of 1.5 g. This is a picture of the facility, the trench, the 70 meters trench, with these active tables. Then they are going to be connected by passive tables, so they can move independently, transfer the motion to the passive tables, and then pick up again by the active. The advantage of having this setup is that we can impose the motion of the earthquake parallel to the tunnel. So that means that if we start the motion of shaking table B a little bit later than A, and C later than B, and D later than C, is that we can mimic a little bit, as I'll show you in a minute, the passage of the shear wave along the axis of the tunnel. Just for scale, you have here, one person to have an idea of the size of the table. So this is the setup. These 4 active shaking tables connected by these inactive or passive shaking tables, and the idea is that on each active table we can impose the motions that we want. We impose the design motions for this particular tunnel, and they can have an offset of time to mimic the passage of the table. So this is a sense of scale. These boxes that are 4 meters by 4.5 meters and 1.2 meters are filled with a model soil, and inside of this model soil we're going to have the tunnel. They are going to be shaken the way that I described, and then we're going to be putting sensors inside of the structure and observe the behavior of the structure. This is my colleague Dr. Yu, that graciously has put himself next to the box to see the scale of what we are talking about. These are done following the similitude relations with a scale in size of about 160, and that means that because the model soil needs to capture, this is very importantly, the behavior of the soil in terms of deformation and in terms of damping. There was a very large trial and error process until this model soil was captured or was decided such that it captured the best we could the response of the field soil. It's a mixture of sawdust and sand, so the representation is fairly good. Same thing with the material that we wanted to use instead of the GINA joints, which are the actual joints that will be placed between segments. So this is one of these small scale segments that were used in the lab for the simulations. So these are all the segments put together. There is a cable outside the settlements that is tension to provide the compression between the segments, and we use a silicon belt to approximate the behavior of the GINA joint. And here what you have is a plot of the load versus displacement, a comparison between the GINA joint and the silicon that was used in the simulations. Again, this is the concept. We impose the design earthquake on the active tables with a time offset to reproduce the passage of the wave. We put all these accelerometers to look at the behavior, and displacement transducers to look at the response of the joints, which is one of the key points that we wanted to find. Here we have plots of deformations, meaning opening or closure of the joint between segments 1 and 2, 6 and 7, 11 and 12. And here what you have is the maximum extension and closure of the joints during the design earthquake, and those were compared with the target values to make sure that the design was adequate. I cannot finish my presentation with a list of collaborators, all have a huge impact on the work that is done. Lots of collaborators from Purdue and the University of Illinois, but I want to highlight the collaboration that is still ongoing between myself and Professor Young and Professor Yu at Tongji University, and particularly the work that they did with the small-scale testing and with the Hcm Tunnel. And with that, I'd like to finish my presentation. I'd like to thank you for your attention, and I'm available for questions. Thank you again.
Thank you, Professor Bovet, for sharing this important information and these valuable lessons learned from studies. So, do we have any questions from the audience?
Hello. Thank you again for inviting me. Apologies of not being there. That certainly was my desire to be able to be there in person, but I guess that next time, unfortunately. Thank you. Thank you. My pleasure. Thank you again.
That's okay.
Evet, buradayım.
A brief verse about Ertuğrul Tacioğlu. Professor Tacioğlu is just the chair at the Civil Engineering Department in UCLA, and then he graduated from the Istanbul Technical University in 1992. Then he attended his graduate courses in United States, and then since 2001, he's a faculty member in the UCLA. And then today he's going to have a nice speech, a nice talk, because I know Professor Tacioğlu is active in research, and then he is leading a lot of projects, and I believe these are the cutting-edge projects, and I will have the fun with you. Professor, it's your time.
Great. Thank you for the kind introduction. Let me just check to see if you guys are able to hear me well and able to see my slides. If I get a green light, I can begin. Fantastic. So many thanks for inviting me to this conference as a keynote speaker. I'm very pleased to be here virtually. I wish I was there in person. It's been quite some time since I visited Turkey. Hopefully in the coming year that'll happen. So today I'm going to be talking about the work we have done over the years towards the development of workflows and tools for regional seismic risk and rapid post-event assessment. And needless to say, this work was helped by countless or numerous postdocs and PhD students. They're just too numerous to name here, so I just want to acknowledge them with my little label. Our work was funded by the California Department of Conservation, the National Science Foundation, Federal Highway Administration, Pure, Caltrans, USGS, and more recently, Digitheon. So just like human beings, structures need doctors. Gradual damage in structures is inevitable. Materials do age. Structures are under permanent and cyclic mechanical loads. They're also affected by environmental factors such as cycles of temperature and humidity. Perhaps more importantly, during the service lives, many structures will suffer some severe event. These could be anthropogenic events and or natural events. Obviously, the focus of my presentation is earthquakes today. So right after an earthquake, we must do rapid post-event assessment. And in case of such an emergency or any similar significant event, we'll have to answer several questions. So three main questions are, if we are operating facilities, transportation facilities, buildings, etc., do we need to stop the operations there? And if so, when will it be safe to restart those operations? And where do we send the first responders? And to be able to answer the first three questions, we actually have to answer a fourth question accurately, relatively accurately. Can we quickly assess the structural damage? And this comes with its own three sub-questions. Is there damage in the system? So that's localization of damage, or detection of damage rather, I'm sorry. And then if there is damage, what are the damage components? That's localization. And the last and the most important question is, how significant is the damage? That's the quantification. So if you have a beam column connection that's cracked, a tunnel lining that's cracked, what does it mean in terms of stiffness and strength loss? So we'll have to be able to answer those questions relatively accurately. So these types of questions must be carried out quickly to minimize the unnecessary downtime. We may have buildings that may have, like hospitals and school buildings, that may have to be occupied and aftershocks might be coming. And the decisions must be made based on quantitative results rather than qualitative results. And wrong decisions can result in obviously disasters. And there will be no time during such an event to do tests. The number of assets, buildings, bridges you may have in an affected region may be very large, and your crews might be very limited resources. And the proposed method, therefore, whatever method you adopt for rapid post-event assessment, must be scalable to large inventories of civil infrastructure. And then the logistics will become chaotic in the aftermath of a major event. So ideally, such methodologies for rapid post-event assessment are somewhat automated so they can be rapidly carried out. The current prevailing practice, even in the developed nations for rapid post-event assessment, is based on visual inspection. And there are many severe shortcomings of visual inspections. They're first and foremost time-consuming and expensive. They will cause service interruptions themselves. And more importantly, they're subjective and prone to human errors. You may be sending two experienced engineers to the same damaged structure, and they may come back with different recommendations. And that is a limitation. Moreover, visual... Sorry. Finally, you may have a lot of hidden damages and invisible damages, and these could be like loss of pretension forces, low cycle fatigue caused by long distant earthquakes affecting big buildings, tall buildings who can kind of shake on two minutes or longer. Weld fractures, damages in the foundations, these will not be visible. So obviously the visual inspection approach will fail in that case. So rapid post-event assessment in the past decades have been pretty much viewed as an option. But I think more and more the stakeholders today are thinking it as a need. And then I believe over time they will become a necessity. So this is because the inventories of complex structures and infrastructure are constantly growing. And then the design philosophies we had are changing from life safety to business and operational continuity. And then there's a realization that the indirect costs are becoming more significant than direct costs. Let me give you an example. If you have a bridge, for example, connecting a major port to its surrounding neighborhood, and if that bridge collapses, the replacement, the direct cost of that bridge might be in the orders of millions of dollars. But if the bridge remains closed for months on end due to the loss of freight traffic, the indirect costs may just well exceed that into hundreds of millions of dollars. So this realization is causing the stakeholders to adopt rapid post-event assessment systems and tools and frameworks, software, including hardware and sensors. And I think in the near future, every new asset that is being built will come with these types of systems built in. So the specifications of a robust structural health and monitoring and rapid post-event assessment system, what attributes does an ideal system should have? First of all, it must be giving you quantitative results. It must be reliable, automated, scalable to large numbers of assets, and it has to give you fast results. And this should help you minimize the operation and service interruptions. It should also help you with preventative maintenance, not just only extreme event, post-event assessment. And also it should be self-improving as you're making more and more observations over time due to ambient vibrations of the system, as well as minor and moderate events. You should be learning more and more about the structure you're observing and improve the predictive capabilities of your rapid post-event assessment system. So over years, we have reached into a solution, we have converged onto a solution that involves the utilization of the so-called digital twins. A digital twin is a digital copy of your real-life asset. And this is typically coming in the form of a finite element model. And an initial finite element model, however, will have differences between from the real life structure. But if the real life structure is instrumented and you're making constant observations, you will have an opportunity to update that finite element model and make its predictions match the observations in the field. And if this loop is closed and you have converged, you will have obtained a true digital twin of the asset with which you can do many tasks, carry out many tasks, including operational assessment, rapid post-event assessment, etc. So our work in this area has been going on for more than a decade, nearing 2 decades almost, and we have published many things to get to where we are today. And I'm going to be showing you some representative results from those. And if you're interested in any one of these things, please send me an email and I'll send you the original references. Our quest has started, like I said, in the early 2000s, and we have begun with the modal identification methods, etc., looking at simple structures and simple damage identification cases. Today, we have reached a solution where we can look at really 3D complex structures and identify damage after major events, as well as even under operational conditions. So we have developed a rather detailed framework to be able to handle multiple types of different structures. So we have a workflow that can handle large inventories of ordinary buildings. For these types of buildings, we do not use a detailed finite element model, but rather some proxy models. And we can make assessments in the case of an event. So this could be a collection of buildings in a region, running into tens of thousands of buildings. And then we also have another workflow that is targeting the critical buildings for which we have a finite element model, and then we iterate on that. This could be hospital buildings and school buildings, etc. And then we also have another workflow for complex structures, including stadiums, bridges, etc. And one of the key components in this is the ability, as I mentioned to you before, is the ability to update the finite element model. And I don't want to get into the mathematics of that, but here's just this little loop that I'm going to talk about to update a finite element model. This is a very sort of complex nonlinear problem. And our approach is to use the Bayesian methodology. So we begin with an initial finite element model whose properties are represented by probability distribution functions. And we make observations of the response of the structure from real life with typically a sparse sensor network. And then if the measurements made at that sensor, at those sensors locations are different than what we have observed, what we have predicted, then we use the Bayesian updating procedure to update those probabilities such that the disagreement between the predictions of the digital twin and the real life asset are minimized. And this loop allows you to not only estimate the variations and changes in the properties due to damage, but also the uncertainties of those estimations. And we have honed these techniques over many projects. I'm going to be giving you like a whole slate of them rather quickly. One project we have done was carried out for the California Department of Transportation, Caltrans, in a bridge in Northern California. This is a water crossing bridge. It has a very complex foundation system, which has seen a retrofit in its recent past. And Caltrans was interested in identifying both the superstructure's properties, but also, more importantly, the dynamic properties of its foundation systems, which exhibit significant nonlinear hysteretic responses. And we have, this bridge was particularly also chosen because it had a number of strong earthquake or moderate earthquake records with which we could do the model updating. And we have created various digital twins of this bridge. Here you're seeing a CSI bridge model, a commercial software, which we have updated using our own software for model updating, wrapping the CSI bridge model inside and doing our updating to minimize the differences between observations and predictions. And we have created a digital twin. We've submitted our report and models to Caltrans, and then we have verified it with existing records, et cetera. But then another earthquake happened right after that in 2014 in Ferndale. And you are seeing the completely blind predictions of this updated finite element model. And the black signal is the prediction of the finite element model, the digital twin, on two main channels of the bridge. And then the red ones are the recorded ones. And you know, I'm skipping some of the details here, but the bridge exhibited significant soil nonlinearity, or experienced rather significant soil nonlinearity in its foundation system during this event. So this is a completely nonlinear model, and you can see its predictive capabilities. These are very heavy calculations. However, advances in cloud computing, parallel computing have more or less you know, eliminated those challenges. These are analyses that can be routinely done these days. Another project we worked on for United States Geological Survey and California Geological Survey was looking at the Golden Gate Bridge in San Francisco. And again, it had numerous moderate earthquakes that it had experienced. And then more recently in 2014 in South Napa, an earthquake nearby in South Napa occurred, and then it shook the bridge. And here you're seeing, and the bridge obviously responded in this really moderate earthquake in a linear way. No damage or significant nonlinearities have been observed. But nevertheless, we could predict its behavior using our updated digital twin. The signals you're seeing on the lower right-hand side, each of those plots contain two signals. One is the recorded, the other one is the predicted. And it's almost impossible just from these graphs to distinguish between the two. That tells you how accurate the digital twin has become in that case. So in our analyses, we do updating using time windows of data, and each block of data is assimilated by our Bayesian updating tool, and then we see changes in the properties that we're updating. So this is another direct comparison of the results that we're observing in this problem. So we've applied our methodologies to other stakeholders. More recently, we have connected up with the United States Geological Survey and the United States Veterans Affairs Administration, and they have approximately 30 hospitals in the West Coast, 27 to be exact, and they wanted to install a rapid post-event assessment methodology framework for their hospitals. And USGS, even before we got involved, had installed sensors in those buildings, and now we're working with them to develop digital twins for some of these hospitals so we can provide them with detailed damage assessment. Another project we are involved in, sorry, my previous recordings are interrupting or interfering with my presentation here. Apologies for that. So let me go. In this other project we are carrying out for the United States Geological Survey also, we are providing with them with additional tools with which they can improve the earthquake early warning messages that they're sending out through their shake alert system. The earthquake early warning system works with looking at ground stations and using some ground motion prediction equations to warn the people in large urban areas of an inbound earthquake. But those predictions are based on only ground motion records, and USGS was concerned about the the validity or the response of human beings to those messages in tall buildings, because tall buildings will amplify those ground motions. And we are in the process of developing some amplification formulas and tools for tall buildings, residents of tall buildings who can get customized messages depending on which floor they are on. And again, this toolbox is utilizing digital twin technology with Bayesian tools. These types of tools are not only valid and useful for rapid post-event assessment for extreme events, but also they can be used under operational conditions. If the excitation source is strong enough, it might be able to tell you, whether you have some sort of a damage, like a delamination of a concrete deck from the girder is happening. In this problem, the major difficulty is also to identify the excitation sources themselves, which provide non-stationary input into the structure. And to overcome that problem, we have combined computer vision, artificial intelligence techniques with our model updating tool. And we are solving, first of all, a problem whereby we use a camera feed to identify the approximate location and class of the traversing vehicles to give us an initial estimate of their loading on the bridge. And then we update the values of those unknown loads together with the properties of the bridge to identify if any damage is happening to that bridge. These techniques, as I mentioned to you, are heavily relying on digital twins, which are computationally expensive. But can this toolbox or can these tools be scaled to large regions? If you're trying to analyze, for example, buildings in a city as big as large as Istanbul, can you do it with digital twins entirely? And the answer to that is not quite. But there's a way to go around that, which is the concept of using fragility curves. This concept, I'm going to summarize it here. Prior to an earthquake, you have many buildings and structures you want to monitor. So you install instruments either at them or nearby. And then using your digital twins, you develop nonlinear structural models of those digital twins and then compute these fragility functions ahead of time. And once you have created an inventory of fragility functions, each of which are expensive to compile and procure, but once they're compiled, they're easy to interrogate. So when an earthquake happens, you can interrogate those fragility functions in near real time. And you can just use the measured intensity measure of the earthquake, such as peak ground acceleration or peak ground velocity, and obtain a probability of damage. And if the damage, and you can do this within minutes if your communication system and computers are up and running. And then depending on the level of damage, you can select a subset of structures for more detailed assessment through the digital twin. And then, of course, then, if you've optimized your computational tasks in this manner, you might be able to provide a really detailed assessment of damage where it is needed. So visually, it'll look like this. You have some sparse instrumentation on your structure. You have already created some initial finite element model, and maybe over time, you have updated the finite element model using moderate events. And then you trust this model. And with that model, using probabilistic seismic hazard analysis, you can develop fragility curves, which will tell you the probabilities of exceedance of various damage thresholds in the building. And then if an earthquake happens, you can immediately interrogate these fragility functions to see if there's any high probability of damage. If there is high probability of damage, then you can activate the more expensive computation and Bayesian updating with the digital twin. We're also working towards technologies whereby we can use augmented reality so that you can use, for example, a headset and inspect a building through the information that is coming from the digital twin. By integrating the digital twin predictions with this augmented reality set, you may be able to even speed up the visual inspections, which you'll have to do anyway. This is an earthquake engineering conference, so I guess everybody's familiar with the fragility curve, but fragility curve, just for those of you who are not quite familiar with it, is a probability curve whose vertical axis is just the probability of exceedance, and the horizontal axis is an intensity measure of the earthquake, peak ground velocity, peak ground acceleration, for example. If the intensity measure is really low, your probability of exceedance is going to be low. If it is high, then your probability will climb up to 100%. And you can obviously create fragility curves for structural components, individual structural components themselves, even individual beam column connections, slabs, and things like that, or holistic fragility curves that'll tell you whether you've exceeded immediate occupancy or collapse, etc. We are indeed in the process of implementing various frameworks, software and hardware systems to several stakeholders in the United States. One of them is the Southern California Water Infrastructure. We are creating digital twins for their above ground water storage tanks. And indeed, we're going to be creating fragility curves for these tanks. In case of a major event, we will hopefully be able to quickly interrogate those fragility curves and classify the damage in the entire region. And if any one of those facilities have suffered or our fragility curves indicate that there's significant damage probability, then we're going to be activating their fragility curves and come up with a more detailed, digital twins, and come up with a more detailed assessment within maybe a day or two of the actual event, or maybe even sooner. So this concludes my presentation. I'm sorry apologize for the mishaps that's happening. My PowerPoint slides were trying to advance on their own. I'm ready to answer any questions you may have. Thank you.
Very interesting presentation. As I have just said, Professor Tajirol is leading the research group, and then their current research are really cutting-edge technologies indeed. Indeed, Professor Tajirol just showed us that the civil engineering is evolving from the very, say, classical way to a very future way. And it's not only the very, say, classics engineering we are doing, but indeed we are really proceeding, stepping into the, say, electronic engineering, computer engineering, and something like that. I believe that this is the future for the civil engineering also. If there's any question from the audience, I would like to really just address to Professor. Yeah, we have one question here. Do we have a microphone there? I think the microphone is on the way.
Thank you for the great presentation. Barış Ünal, Middle East Technical University. I have a question about the updating process of the digital twins. Before you update with Bayesian algorithms, let's say, you are measuring the difference between the measurements and the previous digital twin. How do you select the parameters for the error minimization?
Yeah, that's a good question. And there's a whole lot of detail in there, which itself is a presentation, but let me give you a quick overview of all of that. You can use information theory and obtain, through a sensitivity analysis, obtain the relationship between the sensor density and any given parameter of your selected parameter of your finite element model. And through that study, you can figure out whether something is detectable, identifiable, or not. Imagine that you have like a simple structure like a table with 4 legs on it, and you put only one sensor on top of that table, and then maybe one leg is damaged and you're shaking it vertically or laterally. So with that one sensor, it'll be impossible to localize the damage, right? Which leg is faulty with that one sensor, you cannot do that. So our framework has a built-in feature in it that allows us to relate variations and parameters to sensor readings. And with that, we can figure out what is identifiable, what is not. And of course, we also have structural engineering knowledge of the structure. We know which parameters are important, which parameters are not so important. So we know ahead of time which parameters we are wanting to identify. And then with our Bayesian approach, we can tell whether those parameters are identifiable or not. If they're not identifiable, then we go back to the owner and say, hey, you need to put this new other sensor right here so that we can better identify this property that we're interested in. So that's a short answer. If you want the more detailed answer, I can send you a couple of papers that precisely focus on that question.
I have one question from Professor. Okay.
Good morning, Dr. Taciroğlu. This is Dr. Akbaş from Civil Engineering Department at Gebze Technical University. We have exchanged a few emails inviting you as a keynote speaker to the conference. Thank you very much for this very challenging presentation. We have learned a lot about digital twin technology. My question, just out of curiosity, creating a digital twin model seems to be working very well in the elastic range of the structure. What if the structure is subject to an extreme event, as you have just mentioned, and got into the inelastic range and has some partial damage? How do you update your digital twin model? Do you have to go to the build site for visual inspection and get back to your model, then update your digital twin model? Or do you get some information from the actual structure, the real structure, to update your model? Thank you very much.
Yeah, this is a great question. Our digital twins are actually fully nonlinear. So when we do Bayesian updating, we are updating the nonlinear properties of the structure, not the equivalent linear. Of course, that is possible too, but our full method updates a fully nonlinear model with hysteretic built-in models. For example, plastic hinges in the building models, or PY springs for the pile foundation systems, all of which are nonlinear models themselves. So we're not updating the equivalent properties, like properties of an equivalent linear model, to see how those equivalent linear properties have changed, but rather we're updating the nonlinear model itself. You know, for some structures, equivalent linear approaches might work if you observe stiffness degradation through cycles of loading and damage. Concrete does that a little bit, but then even then it is difficult to correlate stiffness degradation to strength degradation, which is what we're interested in mostly. And for steel structures, even that doesn't happen. The stiffness does not degrade quite as much. So equivalent linear approaches do not work. So remember that little sort of calendar I showed you, like from many years ago to today. So we have all gone through those adventures of trying to update equivalent linear models or doing modal identification to see if changes in the modal properties can be used to localize and quantify damage. Those do not quite work. I mean, there are cases in which you can make them work, but they're not general enough. The general method that we have is based on Bayesian updating, statistical updating, which does not care whether the underlying model is linear or not. Yes, it is a complex optimization problem of sorts, but it is solvable. And you've seen examples of those. Almost everything I show you there had some sort of nonlinearity in it. So I hope that answers that.
Thank you, Professor Taciroğlu, because you're just pointing to the future for the young researchers, and then you're really just pointing something very well for the senior researchers. I thank you very much.
My pleasure. Thanks for inviting me again.
Okay, I think it is just time to the next keynote lecture. So Professor Selçuk Toprak is just going to host the next lecture.
Merhabalar. Bağlantı kuruldu mu acaba? Tamam. Okay. Well, in this keynote lecture, we have a distinguished guest, Jonathan Bray. He is the Faculty Chair in Earthquake Engineering Excellence at University of California, Berkeley. He's a registered professional civil engineer and has authored more than 350 research publications. He created and led the Geotechnical Extreme Events Reconnaissance Association. And this association was instrumental in many reconnaissance studies and provided very useful reports and studies. He's a member of the U.S. National Academy of Engineering and has received the Terzaghi Award, Işıara Lecture, Peck Award, and Joyner Lecture. Actually, he is well known in Turkey as well because of his studies, particular studies related to foundation performance just after the 1999 Kocaeli earthquake. Also, he co-authored many papers regarding the Christchurch earthquake in New Zealand regarding the foundation performance again. His talk today will be related to soil liquefaction on buildings, and we are excited to listen to his presentation, and now we can continue with Professor Bray's presentation.
Thank you very much. It is truly an honor to be invited to give a talk at this prestigious conference. I have great fondness for Turkey. I came after the August 17th, 1999 Kocaeli earthquake, and the countryside, the landscape, the food, the people are just fantastic. So I'm sorry I cannot be with you today, but I really appreciate the opportunity to talk with you. And I will talk about soil liquefaction effects on buildings. Liquefaction effects on buildings are shown here in some pictures from the 1999 earthquake in Turkey, as well as a more recent earthquake in 2011 in Christchurch, New Zealand. Liquefaction can take the soil beneath the building and turn it into a soft, weak material, and we can have bearing capacity failures. We can have buildings slide along the ground. We can have tilt of buildings, and we can have settlement as well as ejecta-induced settlement. We have issues in terms of how liquefaction affects buildings, but buildings participate in this soil structure interaction problem. This is a centrifuge test that's shown here. This is a model building. You can see the ground shaking. The building is rocking itself into the softened material. And so the structure is a key element in terms of loading the soil and making the effects of liquefaction more significant. An example of that in the field is this example in Chile in the 2010 earthquake, where I saw no liquefaction away from the taller buildings. It's similar to what was seen in Adapazari. Wood frame light structures did not put enough load, did not put enough inertia loads into the soil. However, this modern hospital facility, which was built to be in operation after a major earthquake, was not in operation because the 4 to 5 story buildings actually loaded the soil, and the only place I saw liquefaction in this town was where this one tall building was, which loaded the soil. In terms of liquefaction-induced building movements, one of the clearest examples of some of the mechanism is this case of adjoining buildings in the Tohoku earthquake in Japan, a large subduction zone earthquake. This building here is a very tall building on the left-hand side that is on piles. The piles go through the liquefiable fill into the material below. The neutral plane, the seat of loading, is below the liquefiable soil. And so all the indications are is this building did not settle. The ground around it, which was a loose hydraulic fill, did settle. It settled on the order of 300 millimeters. This 3-story building, which was on a robust mat foundation, punched into the surrounding soil an additional 400 meters, such that it settled the 300 millimeters that the ground settled, plus the additional 400 millimeters of the building punch into that ground, so that it settled 700 millimeters relative to the building adjacent to it. A key point here is it's not just volumetrically induced post-liquefaction consolidation settlement. It's also shear-induced settlement as well as ejecta. Looking at the displacement mechanisms that can induce settlement and deformation of a building foundation and affect the building performance, a clear one, a difficult one to estimate, but a clear one is ejecta-induced settlement. If we have ground soil that was underneath the building and now through the ejecta process is on top of the ground, we've literally mined out the supporting soil and we're going to get settlement from that mechanism. During ground shaking, the shear-induced deformations are critically important. In the absence of ejecta, then this will be the largest majority of the settlement. You have bearing capacity settlement where the soft ground and the building will then punch into that softened ground, as well as the SSI ratcheting, which was shown in that video of the centrifuge test. And we also have volumetrically induced deformation, where there is drainage occurring. There's high differential hydraulic heads that are induced by the ground shaking in a loose sand. And so water is moving. If water is moving, then there is some volumetric deformation occurring during ground shaking. But the large majority of it is when we get full liquefaction, the sand rebuilds itself and we get sedimentation-induced settlement, as well as the water pressure leaves the soil, the pressure then is put back onto the soil skeleton and we get post-liquefaction consolidation settlement. These can be seen very clearly in centrifuge tests, where it's very important to capture the volumetric strain responsive soil and it's stress dependent. So to capture the pore pressure response during an earthquake loading, you have to capture the volumetric response of the soil in drain shear. And that can be handled with a centrifuge test. We can take soil and spin it up in a G field at, say, 40 Gs and capture the actual stresses in a soil deposit that's on the order of 20 meters thick. Here we have a couple of meters of fill on top of 3 meters of liquefiable ground. on top of damp sand along on top the base of the centrifuge experiment. This is the input acceleration time history. This is the pore pressures that developed for two tests. One where the relative density of the soil in the liquefiable layer was 30%. Another case where the relative density was 50%. You can see the 30% generates more pore pressure, it's a looser soil, but we still get settlement for the case where there's 50% relative density because we still get pore pressure buildup, which causes the effective stresses to reduce, and therefore the soil softens and we get settlement. The measured settlement for these two tests, as well as a series of other tests of different buildings, is shown here. As a comparison, the green marker is the free field. And so this is essentially post-liquefaction volumetric settlement. But the large majority of the settlement of the building, which is the yellow area here, is this settlement that occurs during strong shaking. Once strong shaking is over, there is this type of characteristic curve that shows post-liquefaction reconsolidation settlement. But a large majority of this is a shaking-induced shear deformation, and the building settles more, significantly more, in the centrifuge tests at prototype scale on the order of 350 to 500 millimeters compared to the 50 to 100 millimeters in the free field. Going now to the field, the recent earthquakes in Christchurch, New Zealand provided a series of examples that could be well documented. One of this was this 6-story building called the CTUC building in the Central Business District of Christchurch, New Zealand. This was measured very carefully with a LiDAR survey, so these measurements are accurate within about 5 to 10 millimeters. There was a pipe that connected this building, which did not settle relative to the ground around it, 60 millimeters. We measured additional settlement, but the large amount of settlement from 110 millimeters to 310 millimeters, the 200 millimeters of settlement was largely over the last 2 bays of this building. So we have the measurement of the south side versus the north side. We can estimate the eject-induced settlement, which was calculated by the amount of sand on the south side. There was no ejecta on the north side. We can estimate the volumetric because there was a bridge not too far away and how much the soil moved, ground moved down relative to that bridge. And then we can back out what the shear-induced deformation must be and get the total settlements. We then, after having these measurements and seeing that this was an interesting site, we then performed field investigations. We started with a campaign of CPTs, cone penetration tests, a very good way of getting the tip resistance, which is shown on the right-hand side, excuse me. And then the left-hand side is something called the soil behavior type index, which gives us a sense of how the soil responds to the penetration of the cone. And it gives us an index of the state of the soil and the type of soil. We did this CPT and found liquefiable soils right beneath the building, as well as some layers that were deeper. We did 7 as well as other CPTs and found that there was no liquefiable soil directly under the building, but there were liquefiable soils at depth. And that's why we followed up later with this additional CPT to see what the difference was between the south and north side, and saw that actually the midpoint of the building was much more like the north side, where there was no shallow liquefaction. And so much of the settlement occurred over the last 2 bays. That's because that's where you have shallow liquefaction with this shallow soil. In fact, there's a geologic map that was done by a geologist in the 1850s named Mr. Black, who showed that there were shallow buried streams in this area. And so a stream channel that's been buried with fill reemerges as a result of liquefaction. We can perform a nonlinear effective stress analysis of this. We're using laboratory testing that we did, testing the soils in Christchurch at the University of Canterbury lab. We are using FLAC, a computer program, a 2-dimensional computer program with the PM4 sand model that Professor Boulanger and Katerina Zipatulu have developed at UC Davis. After calibration with the site information, we can now be bold enough to perform an analysis. And a key aspect of this is this shallow, loose soil on the south side of the building. When we look at the performance of this building, the red is shown for the south side, the blue footing on the north side. And you see the big difference is the shearing that occurs underneath this building. In fact, in the free field, there is shearing, but there's a significant shearing underneath this south side of the building because of the extra load of the building. On the north side, there is no shallow liquefaction, so we get significantly less settlement. There is liquefaction at depth, and that causes the entire ground and building to go down, but we don't get the shearing-induced deformation that leads to the larger settlement on the south side. Here's the estimated settlement on the north side, and you can see the significantly more settlement on the south side. When we look at that, we see that and we do a sensitivity study, we see that our shear-induced settlement is in the range of 100 to 200 millimeters of differential settlement across the building. That's fairly consistent with the estimate of the shear-induced settlement. And we should not capture what was actually measured because part of this settlement was ejecta. And so a continuum-based analysis is not going to capture that. So it's appropriate to not actually capture a mechanism that's not in the program, the computer program. An alternative is looking at this footing 7 building. It's a 7-story building where the building is rocking back and forth, much like that centrifuge test where we saw the building rock itself in. You can see that very closely when you look here where the east side in magenta is moving up. This side's moving up as the west side's moving down. So you can see the rocking of the building into the soil, and the amount of settlement that we calculate is roughly consistent with what is measured. So given that these models and these computer programs and effective stress analysis can capture the key mechanisms, we can now do a sensitivity study and use this as our baseline case with a dense fill on top of the water table, liquefaction in the green layer. In this baseline case, it's 50% relative density. And then we have a dense sand, and below that we have our firm material. We could say it's rock. Then we can do a number of sensitivity analysis. We used 105 different models where we varied the thickness of the non-liquefiable material at top, the thickness of the liquefiable layer, the thickness obviously below the liquefiable layer, the relative density of the liquefiable layer, the building width, the building height, as well as different contact pressures. We're looking for buildings in the range of 2 stories to 8 stories. I feel comfortable extrapolating to a 1-story and 10-story building. The insights from this study would not be appropriate for taller buildings than 10 stories tall. And then very importantly, the ground motions are varied. And we focused on intense ground motions which would cause the most damage to be able to calibrate the effects of liquefaction on the buildings. This is one of the results for the baseline analysis where we have 3 meters of liquefiable soil. This is for ground motion number 4. We had 36 ground motions, but we focused on 12 to really look at the effects of things. And you can see the high shear strains that develop, much like if you had built a building on weak material, soft material, you'd expect the shearing deformation during the settlement statically. Well, if the soil softens as a result of water pressures building up and the effective stress is going down, you're going to get that settlement because of the seismic effect. In terms of looking at the contributions of volumetric strain, which are shown in blue, and shear strain, which are shown in red, both dotted is at 15 seconds. That's at the point of strong shaking in the earthquake. And then at 46 seconds, that's the end of strong shaking. You can see that during strong shaking, a large majority of the deformation that's occurring in that liquefiable layer, which is contributing to the settlement, is shear induced. Even when you get toward the end of ground shaking, still a large majority of that settlement is shear induced. So it's not an overly conservative assumption to focus on the shear induced mechanism governing during ground shaking, and then after significant shaking, focusing on the post-liquefaction volumetric strain. We now do a sensitivity study where we're looking at different factors. One of them is the influence of the ground motion. So this is one of the acceleration time histories. This is the water pressures that build up. They're typically higher under the building because there's a higher contact pressure from the weight of the building. And the settlement for this analysis is shown in black. Previously, we had looked at Arius intensity, but after doing additional studies, we found that standardized cumulative absolute velocity, where you're essentially integrating the acceleration time history, developed a relationship between the buildup of CAV, cumulative absolute velocity, and time, had a shape that almost exactly mimicked the settlement curve. So we're looking at that's the energy that's being put in by the earthquake that's leading to that settlement. After the ground shaking stops, then we don't get that inertia shear-induced settlement. The remaining settlement that's occurring is volumetric. Building contact pressure is an important issue. And as you'd expect, as the pressure goes up, the settlement increases, but to a point, and it actually levels off. And there are cases where the building settles less if it's a heavier building. And this has been borne out by centrifuge tests as well as some case histories. A heavier building may exert enough total stress that the water pressure doesn't get to be high enough to lead to marginal or full liquefaction. So this is actually a real phenomenon. Obviously, the relative density of the soil, the state of the soil is important. These are just focusing on the 12 most intense ground motions. And you can see if we focus on the more intense of those 12 ground motions, for loose soils, we get significant settlement. And then as the soil becomes denser, we get less settlement. But it's not zero. Even a dense sand will undergo cyclic loading that will have moments of building up some pore pressure, which will soften that soil a little bit and lead to a little bit of settlement under very intense shaking. And the thickness of the liquefiable material. As the thickness of the liquefiable material increases, the settlement increases, but to a point. Once the layer is thick enough to encompass the shearing and the large amount of deformation that's occurring within it, doubling the thickness doesn't double the settlement. The settlement of the building is not proportional to the thickness of the liquefiable material for thick layers of liquefiable soil. You just need enough liquefiable soil to allow the mechanism of shearing and volumetric strain to occur within it. So we know that building settlement depends on the relative density and the thickness of the liquefiable layer. It also depends on the thickness of the non-liquefiable crust. We have to, estimate these things. In the laboratory experiments, we could assign that. We could build a soil with a certain relative density of a certain thickness with a certain thickness of non-liquefiable crust. But if we're going to develop a method that can be used in the field, we have to use the tools that are available. And the best site characterization tool for this is the cone penetration test, which gives us a nearly continuous record of the tip resistance with depth. From tip resistance, we have several correlations that can reliably estimate the relative density. You could also use the standard penetration test, but it's not as robust, not as standardized a test. And then we have the factor of safety of liquefaction from our triggering analysis. Every layer now can be defined by its relative density from the tip resistance, the factor of safety against liquefaction triggering from the cone, and a simplified liquefaction triggering method, the depth of the midpoint of each layer and its thickness, dz. With the factor of safety and the relative density, we can estimate a maximum cyclic shear strain potential using the work that Ishihara and Yoshimi developed, which has been put into a CPT program by Zhang et al. 2004. With the shear induced in each layer as a function of that factor of safety against liquefaction triggering and relative density, divided by depth, because we know that depth is critical. The shallow liquefaction is going to cause more shearing deformation than liquefaction at depth. So we deliberately use a 1/z weighting factor. And then the W here is just to eliminate soils that are above the base of the footing. This is what we call the liquefaction building settlement index. Another important issue is, before you get started with the detail analysis, is look at whether you have the chance of relatively low or large strains or large settlement. And much like a crust on top of a soft clay, you can look at a crust on top of a liquefiable material that has reached the residual strength of the liquefied material. And using this closed form solution, we can calculate a factor of safety for kind of a global stability. When we have a high factor of safety, you can get settlement. When you have a low factor of safety, you can get large settlement. There are cases where you can calculate smaller settlements because of things like, for example, the building weight suppressing the loss of effective stress. So the key insights from this study is shear-induced mechanisms govern building settlement during strong shaking. Also ejecta, if that occurs. If ejecta does not occur, then it's going to be largely just the shear-induced deformation. Large building settlements are possible if the factor of safety post-liquefaction is less than 1. The key ground motion parameters are the CAD, which I mentioned, but also the spectral acceleration at 1 second was shown to be important. Key building parameters are the load, but a secondary parameter is the width of the foundation. And then the keep site parameters of relative density and other parameters can be brought in with this liquefaction building settlement index, LBS. So this is the relationship that we developed by developing a regression to the results of our thousands of analysis. It focuses on these key parameters that we've mentioned, LBS, which captures the ground, Q, which is the loading of the building, CAD and SA1 are the ground motion parameters. And very importantly, if you know these parameters, it brings in the uncertainty in estimating the shear-induced deformation in a log normal distribution. Now this is one model, constitutive model, PM4 sand, with one computer program, FLAC. And so you don't want to rely just on one model. Luckily, Professor Dashti at University of Colorado Boulder had done a separate study with a range of different ground motions, actually tens of thousands of ground motions, using OpenSeas, a different computer platform, with a different constitutive model, the pressure-dependent model that Professor Elgamal had developed. If we look at their estimates of settlement versus our estimate of shear-induced settlements, except when the settlements are very low, and we don't care because they're negligible, they track very nicely. So now we have confidence that alternative models are giving consistent results. We also check against the measured settlement in the centrifuge test. We have over 100 centrifuge tests, and what we estimated with the model, and within a factor of about 2. And that's about the best we're going to do on this challenging problem of liquefaction-induced building settlement. We capture what was observed in the centrifuge. But let's go back to the field, because field case histories are the benchmark in which we evaluate any kind of method. This is just some of the case histories that I wanted to point out in this lecture. Let's take, for example, the CTH building during the strong Christchurch earthquake, as well as the less intense Darfield and June earthquake. This is what was carefully measured during these earthquakes. And you can see that the trends from the method are consistent, estimating significantly greater shear-induced settlement for the heavy or the intense loaded Christchurch earthquake, and less intense shaking for the settlement for the Christchurch, for the Darfield and June earthquake in Christchurch. We also included some of the case histories from Adapazari from the 1999 Kajali earthquake. This is the C2 building. This is the observed measured settlement. And this is what the method estimates. So we're getting a tool that gives us a sense of whether we have significant or minor or negligible building-induced settlement. One of the things that's still out there is ejecta-induced settlement. From case histories in Christchurch, where all we've done is taken CPT tip resistance in the upper 10 meters, as well as something called the soil behavior type index, less than 1.8 tells us it's a clean sand, and just plotted the traces in sites where ejecta was observed, it's traced in red. Where there was no ejecta, it's traced in blue. And the key thing that points out is when you have thick deposits of clean sand, you have the potential for a lot of ejecta. When you have layered material where I sub C is going from clean sands to silky sands to clays, you don't have as much opportunity for ejecta in free field sites. Then when you look at ejecta, you realize it is a hydraulic problem as much as it is a mechanics problem in terms of soil response. This is a photograph that was taken minutes after the strong shaking ended. There's not a pipe broken there. This is actually the ejecta coming to the surface because the high pore pressures have found a crack in the surface, and they're bringing the water to the ground surface, and they're bringing the soil to the ground surface. This is a schematic, and when you look at this, this is the hydrostatic case. You have elevation head and pressure head. You have no driving force, but the earthquake generates pore pressures. It's an excess pore pressure. That excess pore pressure is high during the time of significant shaking. If it's greater than the Archesian pressure that's required to bring water to the ground surface, that can lead, if there's a crack, and cracks can develop in the crust, can lead to Artesian flow potential. So we developed a term called the Artesian flow potential, which essentially integrates the difference, the square of the difference of the excess pore head that develops minus that which is necessary to cause Artesian pressures. It's essentially the squared area of this curve. If we look at two sites, we're looking at ejecta at two sites in Craterberry. This is the Shirley site for the Darfield, Christchurch, and June earthquake. And this is the St. Teresa site. This site had significant ejecta for two of the earthquakes. The St. Teresa site, even though it was estimated to have a lot of ejecta, had no ejecta. If we look at the Shirley site and we do an effective stress analysis, this is the soil profile. These are the modeling that's done. This is looking at the displacement time history. This is looking at the excess head that develops. You can see that there's shaking-induced liquefaction at a depth of about 6 to 7 meters. There's high pore pressures that develop the water pressure to go up. It has to dissipate that pore pressure by flowing up. That increases over time. You can see how it's increasing the water pressure right beneath the crust. All we need is for that crust to have a defect or to have some shaking that basically breaks it open. And then there's water at depth that can sustain that water flow. And so if I just move forward in this simulation, we can see that minutes after the ground shaking, the water pressure is still high, and we're going to have the potential for producing ejecta. Compare that to the St. Teresa site, which has soils that can liquefy, but it's highly stratified. We have clean sands, silty sands, a low plasticity silt. The ground shaking starts. It's as intense as it is at the Shirley site. There is some shaking-induced liquefaction, but they're in isolated layers. It actually can lower the demand in the shallower soil that's right beneath the crust that's most likely to produce liquefaction. We have low hydraulic conductivity, silty clayey layers that are restricting the communication of water pressure from one layer to the other. And for the entire time history, this Artesian flow potential remains zero. So the ejecta-induced potential is just the integration of this Artesian flow potential over time. And you can see it for the Shirley site, for the Christchurch earthquake, which led to extreme ejecta, and the June earthquake, which led to severe, and then the Darfield earthquake, which led to none, as well as all of these St. Teresa sites are hidden underneath here because there was no index greater than zero. If we look at the observations of no liquefaction for these two sites under these three earthquakes, we can see that when EPI is low, there is none. When it's a high number, it can be extreme or severe. And this is improved performance compared to something like the liquefaction severity number or liquefaction potential index. Going back to this case history that we talked about earlier in the lecture, let's look at how we can estimate liquefaction in these building settlements using primarily the work of Bray and Macedo 2017, which is published in Soil Dynamics and Earthquake Engineering. First thing, you do a liquefaction triggering assessment, and you find out the layers that can lead to liquefaction. There's actually greater thickness of liquefiable material, but it's at depth on the north side versus the south side. We do a post-liquefaction bearing capacity calculation to get a sense of whether we're going to have lower or the potential for high settlement. The factor of safety is low, so we should expect that we might get significant settlement. Excuse me. And then we use this updated relationship for estimating the eject-induced settlement. There's eject on the south side, none on the north side because it's not shallow. It's not shallow liquefaction on the north side. There's a method that's been available for about 20 years to estimate volumetrically induced settlement based on CPT cone penetration testing. So we're using that method, and we calculate the settlement on the south and north side through the volumetric. And then we use Bray and Macedo to estimate the shear-induced deformation, which you can see is significantly greater on the south side than it is on the north side. And these are the input parameters, and you'll have a copy of these slides. If we add that together, on the south side, the median estimate is 80 millimeters of eject-induced settlement, 200 millimeters of volumetric, 180 of shear. The total is 460 millimeters. The range is 300 to 600 millimeters. On the north side, there is no ejecta. The volumetric is a little bit less, but the shear is significantly less. And so you get a median estimate of about 220 millimeters. So what matters most to the building is differential. The estimated median differential settlement is 240 millimeters. And the observed in this case was 250 millimeters. Now, I do not guarantee this level of accuracy in all cases. This is a difficult problem. This is one of the better case histories, but if you look at the paper in Soil Dynamics and Earthquake Engineering, you'll see that this method can estimate settlement within a factor of 2 and allow you to make good engineering decisions. So in conclusions, liquefaction-induced building settlement is caused by ejecta, shear, and volumetric mechanisms. The shear-induced mechanism governs during earthquake shaking. Also, there'd be ejecta. We talked a bit about eject-induced settlement at the end. Our new procedure captures the shear-induced settlement, as well as the uncertainty in making that estimate. It provides results that are consistent with 19 field case histories that are carefully documented, the 100 centrifuge tests, as well as thousands of dynamic SSI analysis, not just the ones we perform, but others performed by Professor Dashty and her team. And then the eject-induced settlement is realizing that soils can liquefy, but the sites that produce massive amount of ejecta typically are these thick, clean sand sites. Thank you very much.
Well, thank you for the interesting presentation in the sense that actually there was a need for particular applications or methods to analyze buildings in liquefiable soils, and I think the research presented by Professor Bray light a particular light on this issue, and this is very important. Can we have Professor Bray also on the screen? Or okay.
Well,
You hear me?
yes, thank you.
All right.
I do.
Well, let's have the questions from the audience. Meanwhile, while waiting the questions from the audience, I have a question, actually, particular question also. When you mentioned those, liquefaction building settlement index, you utilize, you can utilize different methodologies for liquefaction triggering. Do you think is this important in your evaluations or in this index parameters?
Yes. The method that's most widely used around the world is the Boulanger and Idris 2014 method. It was also published in a journal paper in 2016. It has important case histories and insights, and it provides good information. Now, there are alternative methods that are equally useful. Under Chetan with Ray Seed have a method, as well as Peter Robertson. So it's good to use a baseline analysis and then use at least one or two other methods. If they agree, you feel comfortable. If they disagree, then you have a chance to think about why they disagree. What are the things that are leading to that? Even more important than the method is the procedure used in the field. That's cone penetration test is far superior to the not so standard penetration test. And so I really encourage, especially in Turkey, use of the CPT. It is more reliable and it provides a consistent, standardized way of getting that tip resistance, which is so important as an input to the simplified liquefaction procedure.
Regarding the foundation performance during the Kocaeli earthquake, you are quite familiar with the site investigations in Turkey. I think your insight is very important in this regard. Thank you very much. Do we have any questions? Okay, then my second question comes. If you don't mind, Professor Bray. You mentioned some finite element and finite difference analysis, in your talk. One was involved on PM4 sand model with FLAC, and then open seas with PDMYO2. And I wonder, do you recommend actually use of those methods in real practice? Of course, they are complicated, but you present a usable practical method. But I just want to get your opinion. Maybe the audience in YouTube and in here can have your insight on this topic.
I strongly urge application of effective stress analysis. You gain so much insight in terms of the mechanisms. For example, the evaluation of whether we're going to have ejecta, what layer liquefies, how it affects the system response of the soil, how water pressures move. That can only be gained by doing an effective stress analysis. Now, I realize as a practicing engineer that you often don't have the budget to do a full analysis and all of the testing required to calibrate the model so that you trust the model. So that's one of the reasons why we did thousands of flak analysis with PM4 sand and took advantage of the 10,000 analyses performed with open seas, is to come up with a method that can find the key issues and allow you in a practical sense to use basic data to make estimates of how much settlement will occur, and be comfortable that if you had done a flak analysis with PM4 sand, you would have gotten results that are consistent with what we got. But the insight that you gain by doing the analysis is as important, if not more important, than the results, because that's why we do analysis. It's not really to get the answer, but to gain insight and understand the key mechanisms so that we can make good engineering decisions. And it's useful when we have an idea of what the answer is and we can understand what the answer is sensitive to, but it's most important to see the effects of the earthquake and understand what's happened in our sites. And that can lead us to developing more effective strategies for mitigation or retrofit or design to eliminate the issue in the first place.
For very valuable comments and your presentation, Professor Bray. Actually, we will be very happy to have you here, if the conditions were suitable. That was our desire from the beginning, but it couldn't happen. Maybe in near future, we hope to have you here in other occasions. Thank you very much.
Now, I have tremendous respect for the engineering seismologists and the geotechnical earthquake engineers and the structural earthquake engineers in Turkey. And unfortunately, we've been challenged by some severe earthquakes, but we've grown and we've learned from that. We've learned together, and the partnerships between Berkeley and the US and Turkey are incredibly valuable to us. And thank you so much for inviting me to give this talk.
Thank you. Thank you. Well, I think now we will continue with the next keynote lecture. Thank you for your patience, by the way. We are changing, but you are always there.
Yaklaşık bir seneye varan bir süreçti bu konferansın hazırlanması için bizim aktif olarak çalışmamız. Ve açıkçası tüm ekibin de beklediği bugünün açılışıydı ama sanırım şu anda çok daha başka heyecanlı bir yere gelmeye başladık. O da ilk günün sonu. Şimdiki konuşmacımız bugünün son konuşmacısı olacak. Keynote Lecture son konuşması yapıyor olacak kendisi. Ve açıkçası bizim uzun zamandır, gerçekten de bir yaklaşan zamandır beklediğimiz ilk gün birazdan bitecek. Birazcık daha lütfen sizlerden sabır istiyor olacağım. Çünkü oldukça geç bir konuşmamız geliyor şu anda. Bağlantısı hazır mıdır? Süper. Gayet iyi. Let me introduce you to Professor Anastasios Sextos. He's a professor, and then he attended undergrad education in Thessaloniki University. In 1997, he graduated, and then he attended his second degree in University of Bristol. And then later on, he completed a PhD again in Thessaloniki University. And then for the last 4 years, he's been working in the Bristol University. And then he is actually really, again, active person in the research. And then he is leading very, very, interesting researchers in the University of Bristol. He's also the chair of the Hellenic Association for the Earthquake Engineering. And then actually we had the chance to work in the Samos earthquake for the last year indeed. And then he's also in active development of the Eurocode 8 guideline. And then he's going to present a very lovely presentation indeed. And then I think it's just time we can go. Yeah, okay.
Good evening, ladies and gentlemen. My name is Anastasios Sextos. I'm one of the speakers for this evening. First, I would like to thank very much the organizing committee for inviting me to act in this capacity. I'm delighted to be speaking in this very important conference, Without further ado, I would like to share my slides and start talking about a quite challenging topic that deals with the seismic response of long bridges. Obviously, we're going to be dealing with extended structures that are subjected to ground shaking of some great intensity. And we will also be dealing with pipelines as well, because these are also some structures which seem to be responding in a rather simpler manner, but effectively there are cases where the seismic demand can be quite surprising. So I'm going to be presenting you field evidence, large-scale testing, and particularly some Eurocode data implications, because research should be also be practicable to be used in real-life applications and in design. Obviously, I don't have to tell you much about how beautiful bridges are. You have some really amazing bridges in Turkey, in the seismic prone area in Europe, I would say. So there's no surprise that these structures, as you know very well, require a very careful design. However, there are some aspects of their design that we tend to neglect, and one of these is effectively the way we consider for the fact that ground motion is different across long bridges. And it is different in terms of frequency content, in terms of phase, in terms of amplitude, for reasons that are quite simple to understand. So there's actually no question about what I'm going to show you. Everybody believes that ground motion, is different in space, in time. However, sometimes the problem it is perceived as too complicated, and therefore we think that it's better that it's more certain, let's say, to do nothing rather than dealing with the problem itself. So let's go and get down to the very basic sources of especially variable earth-to-ground motion. And we will first start with what is obvious, that it takes some time for the seismic waves to arrive at different points. This is called the traveling effect or the wave passage effect. We'll be dealing with it. It's the simplest version of time delay we can assume for our structures. Clearly, it's not enough. However, it's one of the fundamental things that we can easily understand. And of course, we may guess, even if we're not really very much in the bridge design, that ground motions can arrive at different times, but they don't necessarily have to be the same, because waves, as they travel through the soil media, they get reflected, fracted, superimposed, and therefore it is very natural that the ground motion wave that we will record in point X is going to be different, not just delayed. It's going to be different compared to the ground motion we recorded at a point Y. Therefore, there are several techniques that aim to quantify what is called the coherency or the incoherency of ground motion, which is actually the lack of statistical dependence of correlation, like between ground motions between different locations. And of course, when there are abrupt changes in local soil conditions, let's say stiff soils at the abutment, soft soils in the middle of the bridge, it is very natural that the local side effects are quite different, and therefore, even if the motions were basically the same at the bedrock level, they naturally tend to be different, again, in terms of amplitude and frequency and content at what is called the foundation input motion at the base of the structure. This would be valid with or without special variability, and of course, it's even more prone in case of multiple support excitation. For long bridges crossing river valleys, it is also very common that some part of the bridge is subjected to liquefaction. Therefore, ground motion by default is going to be way different in this location compared to others. So there are several ways and reasons why ground motion would be the same. And after all, the final one is that simply as they reach the foundation levels, because the foundations can be different, because the motions are different for the reasons I've explained so far, and because the whole soil structure interaction problem is frequency dependent, it is really natural that kinematic interaction and inertial interaction is going to be frequency dependent and support or peer dependent as well. So there are at least 5 reasons why ground motion should be the same. Now, whether this is good or bad, it's a really very open discussion, and I hope that by the end of this talk, we will have some answers to this. But first, let me try to convince you a little bit more by showing some observed or measured evidence from the field. Observed is typically the unsetting of bridges that we have experienced in the US, in Japan, and in other places in the world when the seating length is not adequate and because there is differential motion among different piers, it is very natural that the seating length is exceeded by the displacement of the deck and therefore it collapses. There is no better evidence than showing this for justifying the fact that ground motions vary among different pier foundations. And then, of course, there are measurements in seismic arrays. It started from Lutung, Taiwan. There are hundreds, probably maybe not hundreds, but around 60, 70 sites all over the world that measure the ground motion after certain earthquakes. But this provides a very well-controlled piece of evidence because motions are recorded for the same event and then they are compared. And by being compared, it is possible then to try to derive some patterns. And the most important pattern that is widely accepted, of course, in the literature is that this coherency that I just talked about, which is, as I said, the statistical correlation of ground motions, basically reduces with frequency and with distance. So the higher the frequency, the higher the drop rate. The higher the distance, the higher the drop rate. Now, how high depends on several parameters that affect the exponential decay of this coherency function, but this is effectively the way we consider that motions become more and more different the more the points are separated from the source. And then there are several functions that describe this drop. You can see that there is a scatter among them because they have been either developed analytically using other assumptions, or they have been measured or recorded in different accelerometric arrays around the world. Overall, you get an idea that after 2-3 hertz and after, let's say, a distance of 200-300 meters, correlation is about 50%. So just to give you a rough idea about what we should be expecting. Let me also show you some examples from things that have been measured. This is the Chalkida Bridge in Evripos Island, in Evi Island, excuse me, in Greece, which is a quite long bridge, about 700 meters, with a central cable stayed part of about 400 meters. That has been permanently monitored by the Institute of Technical Seismology and Earth Engineering of Thessaloniki in Greece, and it was able to record the earthquake of 1999. This was a 5.9 earthquake, magnitude earthquake, that occurred at about 50 kilometers from the site. So naturally, ground motions had a low amplitude of about, let's say, 20 centimeters or 40 centimeters per meter squared. This is the acceleration. But this is actually good because it didn't trigger any linear response of the bridge, and we can be certain that whatever has been recorded is actually linear. And by that, by looking, of course, where the accelerometric arrays were responded on the bridge, and after clarifying that because obviously the accelerometric stations effectively also recorded the vibration of the bridge in a sense of inertial interaction, if you like, all this has been filtered because, quite easily, I would say, as the frequencies of the bridge are quite far away from the frequencies of the dominant frequencies of the ground motion, and therefore this uncoupling was made. But to cut the long story short, the idea here is that we were able to measure the Earth, the free field motion, if you like, and also the response of the superstructure, which is something quite rare, I would say. We can see measurements on pier number 4, number 5, 6, and 7, and then we were in position to compare them and actually try to understand how the response was different, whether detrimental or critical, we have to check, with respect to the actual uniform scenario of uniform excitation. The problem by doing this comparison is that uniform excitation does not exist in the field. So there is nothing really that we can compare against, in fairness. But we can probably assume that we can take the motion at, let's say, pier M4 and assume that this is uniform and apply it uniformly across the bridge. That's the only comparison, meaningful comparison we can actually make. But there's something very interesting to see here. Let's take, for example, I'll show you just one example because this is a good and interesting characteristic of what asynchronous motion or multiple support excitation can trigger. So let's take the sensor number 5 here, which records the vibration of the bridge. We can plot the Fourier transform of the recorded acceleration for the actual asynchronous motion, and we can do that also numerically by assuming a uniform scenario using a finite element model that is calibrated to match the measured response using a multiple input, multiple output optimization scheme. With this approach, we are able to plot not only the time histories and verify that the ones we get numerically are the ones that we see, we recorded on the bridge, but we can also plot on the frequency time scale the frequencies that are triggered for these two very different scenarios. What are these two scenarios? The synchronous excitation, which, as I said, does not exist, but we figured it out by assuming that we've got a single motion applied uniformly. The first motion is real, but we're assuming that this is uniform across the bridge. And then we have the asynchronous excitation as measured in terms of excitation. And this is the frequency time space response of the structural behavior, of the acceleration actually at this very sensor of 5T. You can see that they look alike, but effectively there is an extra frequency or vibration at the specific triggered frequency that was not visible under the synchronous excitation. And if you go and plot the Fourier transforms in the standard frequency domain, you will see that there is a frequency here around 4 Hz that has been excited, which actually means if we go back to our finite element model, we can see which this mode is. We can see that this is an antisymmetric mode. And if we go and examine in more detail the design quantities of interest, like bending moments, displacements, and so forth, we will see that effectively almost all the displacements of this particular peer have been increased, and the bending moments associated with these particular peers have also been increased just because of the triggering of this Hcm mode. So this is the #1 feature of special variability. It triggers Hcm modes, and this will get along with us quite extensively in this talk, because this is, I think, the key aspect for understanding what is the main implication of synchronous motion. So we keep that in mind, and we move further and see some numerical evidence. Numerical evidence means that we will solve the problem analytically and using finite elements, and we'll be running several scenarios by producing realistic ground motions, considering all the effects that we talked about: wave passage, loss of coherency, side response, kinematic inertial solid structure interaction. So for the case of a structure that is multiply excited, apparently the equation of motion is a little bit more complicated because it involves degrees of freedom that are unconstrained. But effectively, it is not as complicated to solve it, because even in standard, let's say, books like Clough and Penzian or Chopra's book on dynamics, this is really known how easy it is to substructure a problem into a pseudo-static component, which effectively generates the quantities that are associated with the differential movement of the foundations, and the dynamic component, which is exactly what we just saw, the excitation of Hcm modes, or even the reduction of the response in specific modes. And by doing so, one is in position to derive ground motions, simulate, if you like, all the physical phenomena that I discussed previously, to simulate ground motions at different locations, and then by the dynamics that I just presented, to calculate the response of the structure, or simply solve it in finite elements and find the response in numerically. But in doing so, in simulating the ground motion, let's say at the base of an extended structure, one has to decide in advance what would be the target frequency content. This can be done by using code spectrum, a standard reference spectrum from an actual ground motion that I've recorded in the past. You can use a standard power spectral density function, because that's the way it is introduced into the problem. Let's say using the Kaneda-Jimmy power spectrum, which is quite extensively used in dynamics and random vibrations, adjusting it for the properties of the local soil, for instance. But at any rate, to simulate ground motions and the multiple support excitation of a structure, you actually need the target frequency content in the form of a power spectral density function, which looks pretty much something like this, shifted left or right, depending on the soil. And then you see, I just give you directly that there is a solution in the time domain, which is actually what we need. There is a solution which is the double sum of things that I'm going to talk to you in a while. Theta corresponds to the time delay, so it's easy to be calculated. Phi or phi is a random angle that produces some stochasticity into the signal. Otherwise, every time we would press in the computer, we get the same ground motions. And then this LJM is the triangular matrix that results from the Cholesky decomposition of this very important cross-power spectral density matrix, which exactly controls the correlations between the two motions. So it says that all motions along the diagonal, so in comparison with themselves, have the same frequency content, but the cross terms don't have necessarily the same amplitude in all frequencies, because this is controlled by how far they are and the specific frequency given the target coherency that we have assumed. So with that in mind, all terms can be calculated, as well as the function A, which is an envelope function that we simply multiply the ground motion so that we make it look like an actual ground motion, ramping up gradually, then having a main ground motion intensity part, strong intensity part, and then decline to look like an accelerometer. So with that, it is possible to generate ground motions numerically. And of course, this can get very complicated. I just give you a reference here from a method that we have developed in the past that accounts also for side effects and SSI and so forth. And there are more elaborating methods, more advanced methods like the side-dependent spectra by Shinozuka and Diodadis, where in each point you can have different spectrum and therefore different frequency content, and all together they follow the same coherency loss pattern. So all in all, they're correlated as planned. With that, somebody can run analytically the structures, hundreds of structures, thousands of bridges, as I'm going to show you, and obtain some fundamental results. So I'm going to tell you straight off what we do know already, leading to one additional thing that I think we found quite recently, and it's interesting to share. So one thing that we know is that spatial variability is quite complex, as you already guessed. It's frequency dependent. More uncorrelated motions don't necessarily produce the most critical structural response, which actually means that there is a case that spatial variability is very important in terms of how different ground motions are, but the response of the superstructure is beneficial. That's very, very common, and I'm going to show you why. And thirdly, that in most cases, we cannot assess it in advance, which means that we need to do something else. That's actually my proposal at the end. Some examples. Already, I think I've explained that it is such a case-dependent problem that we need to address it in a probabilistic sense. Therefore, let us see a large number of bridges. These are all bridges located in Greece along the Egnatia Highway, most of them. The highway connecting the Greek-Turkish borders with port in the Adriatic Sea in Igoumenitsa, northern Greece. So there are several very interesting and challenging bridges, quite long as you can see here, that have the chance to have access to their design drawings. We work with the highway very closely to model them, simulate them in various scenarios. So we have a quite representative stock of long bridges in the seismic region and overpasses as well. And then we're going to be plotting, let's say, a simple ratio, the response of the structure, whatever this is, a design quantity, bending moment, shear force, displacement, drift, ductility demand, due to a synchronous excitation over the synchronous. Whenever this is more than 1, obviously the impact of spatial variability is critical. Whenever it's lower than 1, it is beneficial. And this is just the first statistical evidence of this ratio. Therefore, whatever is below 1 is beneficial. As we are increasing the wavelength, you see that statistically, until about 400 meters, spatial variability is globally beneficial. The ratio is less than 1. But here, we're only looking at the simplest case of wave passage effect. So we have just the same signal arriving at different points at different times. And for that, there is a simplified, let's say, observation that it would take about 400 meters for this problem to be statistically important for design. That's the good news. The bad news is that wave passage effect alone never actually exists in reality. And it's going to be interesting to check another bridge, not from our region in the southeastern European area. Let's go to Austria, for instance, where seismicity is not as high. But that's an interesting case because that's also a monitor bridge and the finite element model had been calibrated and validated using an optimization scheme. So here we are seeing the same ratio in terms of bending moments, but not only for the case of wave passage, also for the cases of lack of coherency or the combined effect. And you can see that it can easily get more than 30%. So bending moments can be more than 30% for a bridge that was about 200 meters actually. And this is quite an interesting result. And by looking again more specific responses of a specific pier, let's say pier 5 in this case, and by plotting, let's say, the acceleration over a period, this Fourier spectrum, but expressed in terms of periods so that we understand a little bit better, for the synchronous excitation, which is the standard one, the black one, and then in coherency only, it's going to be the red one, and the combined is going to be the gray one, you can immediately see that again there is a mode that has been excited. Which mode? The antisymmetric mode. Because the first one, we recognize it, this is being reduced due to asynchronous excitation, and that's quite natural because multiple support excitation effectively obstruct the structure from vibrating at its fundamental mode. That's very typical. So the response in the fundamental mode is reduced, the response in the third mode is reduced, the symmetric mode, the response in the antisymmetric mode is increased. So again, it's a matter of the frequency that is excited. Because we were looking exactly about a pier which is located in this region, and because of this mode, its response has been increased. If we were looking at a pier that was located pretty much in the middle of the bridge, which was not affected by the antisymmetric mode, very naturally, the effect of multiple support excitation would be beneficial because there would be no increase by the excited mode, but clearly decrease of the response because of the suppressed fundamental mode. So it's an interplay depending on where every component belongs in terms of the dynamic properties and the modes that are excited or are not excited due to spatial variability. Just to visualize this a little bit better, the same bridge, we apply the ground motion synchronously, and we apply the ground motion asynchronously. You can see the response just visually, actually. You can see that the asynchronous comes at a delay, okay? That the excitation under the synchronous response pretty much resembles the fundamental mode after some point, whereas the response due to the asynchronous excitation, it looks like a propagating wave. And you can even visually see that the synchronously excited structure vibrates basically in the fundamental mode, whereas the asynchronous one oscillates primarily on the antisymmetric mode. This is even visually seen from a simple video of the response where, of course, all modes contribute in time. That means that the effect of the triggering of excitation modes, it is really dominant in the response, if we can even visually see it without any Fourier. And this is why our efforts have been concentrated in looking at this problem more extensively. These are the numbers, but I think you've seen it with your own eyes. I don't have to show how modes are suppressed and how modes are excited. This is pretty much what we have just seen from the video. Now, how systematic is this excitation of our modes? Let's take another bridge. That's an interesting bridge because it's seismically isolated. It's called Lissos Bridge in northern Greece as well, in Thrace. And so for this, we're going to do exactly the same. We're going to plot the asynchronous over the synchronous ratio for bending moments and displacements to assess whether spatial variability is critical or not. And we're going to be checking how many modes are excited for each scenario. What do we mean by excited? It means that the Fourier amplitude is more than it used to be for the synchronous case when we're running it asynchronously. And of course, that we're talking about a mode that it is important enough by mobilizing by more than 50% of the modal mass, for instance. So it's not a negligible mode. And by doing so, you can again see, I'm not going to get into detail, how specific frequencies are triggered, specific modes are triggered, and this is what actually leads to specific Fourier amplitude increases that then lead to maximum displacements that are higher. This is just a snapshot, an example, before we go to the statistical processing. Because in the statistical processing, it is even easier to observe what is actually justifying that higher modes are excited. For instance, what we're plotting in the vertical axis is the displacement over the asynchronous case, of the asynchronous case over the displacement, transverse displacement of the deck of the synchronous case for each different peer. Whenever it's higher than 1, the bending moment or the displacement in this case is higher. Wherever it is red, it means that there is an associated mode that is excited. And we can easily see that for all peers, the percentage where higher modes were excited, in most of them, are more than 50%. And very naturally, this does not apply to the middle ones, because you can guess already that the middle peers are not that much affected by the antisymmetric mode, the first antisymmetric mode. And it's also very interesting to observe if a case, in case of that a mode is excited, how probable it is that this will lead to an increase in demand. So that's the conditional probability that the mode is excited. Given that the mode is excited, how probable it is that this ratio is higher than 1? Well, highly probable. 70, 50, 80, 90, 100%. So whenever we've got local critical response due to special variability, 70, 80, 90% of the cases, it's because of asynchronous excitation, excitation of higher modes. This is really important. And of course, the same applies to the activation of stoppers, because this seismically isolated bridge has a number of stoppers. And these stoppers are activated more for the asynchronous case and more often, not so often in the middle peers, because in these peers, the antisymmetric mode is not doing much. So everything comes into one picture, I think, and explains quite well something that looks very difficult to explain and very difficult to predict. And it's also interesting then to plot the results in terms of the fragility. The fragility is going to give us the probability, of course, of exceeding a specific damage state given the period, the spectral intensity measure, in this case, the spectral acceleration, the first fundamental mode. Here you see the dotted lines which express the fragility of the special variability case. They are not very different. And this makes us think why they are not so different, since we have already observed that there is excitation of higher modes and there are cases where the local response is increased. Well, this is because the fragility is working with mean values, and therefore some outliers of local response are suppressed. Here the damage state maybe is controlled by a specific damage in a specific peer. Maybe we take the envelope of multiple damage modes. Depends on the way we construct the fragility curve. So statistically, I would say that special variability leads to either beneficial or negligible increase in structural demand globally, but locally, it might increase the seismic demand really substantially. And whenever this happens, this is associated with higher modes. This is quite safe, I think, now to conclude. Another example here for the excitation of higher modes, that's the Menidi Bridge. It's also fully seismically isolated in the Ionian Highway. I'm not going to get into details because you're all very experienced to understand the structural system, the base isolation, how we generated ground motions. We run the examples. You can see how motions are different among different points. This is just a snapshot. Again, very different response, much higher seismic demand in the bearings. This is quite systematic in all bearings under all intensities of PGA. For the asynchronous case, the blue one is the ductility demand is much, much higher. And you can see that it's almost always than 1. The displacements are almost always, but it reaches more than 1, because in this particular case, as it is fully seismically isolated, almost all modes are excited, at least in the frequencies of interest. So this is a case where it has been globally problematic. And that's another interesting case of a curved bridge in Krystallopiki next to the Greek-Albanian borders. It's a 680 meters bridge, again, of the perpendicular axis of the Ignaria Highway. I'm not going to get into the details. I'm just going to say that in this case, because it is curved, we also have to consider the angle of incidence and special variability. And I'm going to get you directly, not even to fragilities, directly to loss. So we accounted for the repair rates of every single damage mode that we have seen. And therefore, we will be able to calculate the associated loss. Direct loss, structural loss, not indirect due to downtime. All right. But this is also very clear here to observe that this is the loss on the right associated with the uniform excitation, and when we consider the wave passage, this is not affected that much for abutments, bearings, and piers. But when we come to the holistic introduction of special variability, the cost can be substantially increased, mostly for the bearings, because half of the supports of the deck on the piers are on bearings, and the cost of repairing the damage of the piers themselves, it's almost double. So that effectively aggregates all the uncertainties associated with our statistical processing and special variability. If we get down to loss, it's gonna be more expensive to repair in most of the cases, irrespectively of the fact that maybe globally in some bridges the response will be beneficial, for instance. Particularly curved bridges are highly sensitive to special variability. Therefore, with all this evidence, I think I have demonstrated our idea, which is actually that it's pointless to try to predict ground motion. You can run a number of scenarios if you have the luxury to solve the problem probabilistically, yes. But we are proposing, and in fact, when I'm going to show you a summary of this, it's going to be seen as one of the possible solutions in the revision of the Eurocode 8. So in our approach, which you can find in the relevant publication, we argue that we don't have to model necessarily all the scenarios to account for special variability of earthquake ground motion, because then if we design with the mean values, the extreme effects that are observed locally will be suppressed. Therefore, we take it as a given that one of the possible ground motions can excite higher modes, and we focus only on the structural elements which are affected by the excitation of this specific antisymmetric modes. And to do that, we subtract the problem into 10 steps, starting from the very simple, let us set up a target frequency content in the form of a power spectral density function, like the one that we discussed previously. Step 2, let's get the modes of the bridge to see which is the first, let's say, antisymmetric mode, like the one that you can see here, for instance, or others. Third is to derive what is mathematically quite easy, the influence matrix. So we move by a unit displacement statically its foundation, and we measure what are the displacements in all other degrees of freedom. Fourth, we calculate the modal participation factors associated with this support excitation. As a next step, we can calculate a matrix which effectively represents how motions vary in the frequency domain in relation to the known motion, which let's say it's assumed to be in the abutments. And there are some simplified expressions to do this, introducing just properties of the soil and the distance. And then we can plot here the excitation of all modes. To progress in a quicker way, we can effectively identify some amplification factors per mode. These are examples, for instance, that for this specific mode, the antisymmetric mode, in these frequencies, these are the frequencies where the mode is associated with. And then we can just say that, yes, but our structure is not necessarily interested in all frequencies that a mode can be excited. It is interested only on specific frequencies that are actually associated with the soil profile and the properties of the bridge itself. So with that, we end up with amplification factor for specific modes. We then run a set of, let's say, pushover type analysis in the perpendicular direction, applying the profiles of the antisymmetric modes with the amplitude of the amplification factors. We measure displacements and design quantities and bending moments, and we superimpose with a uniform case. And because this is a research paper, it's not design, the simplified version for design, after hundreds of statistical analysis, is that, okay, you can just keep everything. You can assume a safety factor of 4 and a safety factor of 2 for the first and the second antisymmetric modes. You take the antisymmetric mode profile, you run the pushover with this amplitude, you measure the design quantities statically, and then you superimpose with the dynamic design quantities. And this is going to give you, obviously, an increase only at the elements, the components of the bridge that are associated with the higher modes, assuming that At some point, this will be excited by some ground motion. So this is a very tailored, peer-dependent amplification factor, not a global amplification factor for the entire bridge. Example how well this works, we compare this method with very rigorous numerical analysis for two bridges in Lissos and in Metsovo, and you can see that effectively the new approach, which is the orange one, meets pretty well what is measured from very refined numerical analysis for both structures, which is actually quite promising. Finally, spatial variability is very challenging and important for bridges. Is it important for pipelines as well? Well, if you ask in the audience, I guess 95% of the people, including myself some years ago, I would say no. And I would say no because pipelines can be subjected to fault rupture, can be subjected to local deformations, but transient response dynamically, I wouldn't bet that it's so important, simply because a pipe doesn't have enough mass and it's not really stiff to have any effects from the traveling waves. It goes with the ground, to put it simply. However, there are cases of geological or geotechnical discontinuities, like the ones that you can see here, that if you run it numerically, you can see some quite extensive increase of axial strains at the boundaries of the discontinuity. And this explains damage that we have seen in the past of buckling of pipes at some locations, even upheaval of pipes outside above the ground, that is quite spectacular. And these were not attributed to fault crossing. Therefore, we thought to give it a try and solve the problem in more detail. We solved it, of course, in the far field, and then in the near field, we modeled it in the most rigorous way we could, involving the consideration of buckling of the pipe and friction at the pipe-soil interface and non-linearity of the ceramic soil within the trench. And with all this substructuring, we ended up with some quite substantial verification of the increase of strains, as I just said. That was too substantial to believe, and therefore we decided to have a decent test on the shaking table of the University of Bristol. So we used the shear stack filled with soil with appropriate similitude laws, introducing a pipe within soils that had different properties. So this is the, let's say, the geological or geotechnical discontinuity between dense sand and less dense sand. We use fiber optics to measure accurately the axial strain, and then we subjected the whole thing of the shear stack into ground motion using the shaking table. And you can see here that the axial strain is actually quite substantial exactly at the locations of the boundaries. And if you roll back the similitude laws and calculate the problem at the prototype, we verified what we analytically predicted, that this can actually lead to buckling of pipes because of the different soil properties and the abrupt change of geotechnical conditions. A final case of spatial variability of a pipe, but in this case above ground pipe, a linking pipe, if you like, connecting two buildings in a compressor house. In this case, where is spatial variability arising from? Since the two structures are located quite close one to each other. It arises from the fact that because they have different frequencies of vibration, they have different fundamental period, they're actually vibrating out of phase. Therefore, the pipe at its two ends is subjected to differential motion. So that's an above ground type of spatial variability for a pipe. And to solve this problem, we substructured it again into a physical problem tested in the laboratory of the University of Patras, where all the rest were run numerically at the University of Bristol. And we ran a hybrid test. I'm not going to get into the details of it, but you can understand that there is an analysis coordinator that's actually exchanging information between the displacements that are applied and the reaction force that is measured, that then is fed into the system in every time step. And in this loop, the numerical module interacts with the physical component, let us say. So in this case, you can see pretty much the displacement of the measured displacement of the elbows. Naturally, in this case, all the strain, it's not going to be axial. It's going to be around the bends, which are the most sensitive in this particular industrial application. And this also showed an increase of about 40% of what we would be expecting if the two edges of the pipe were located in buildings with the same frequencies. Of course, the solution here would be to provide sliders and at least avoid fixities of the pipe on the two buildings. So to conclude, first question was, is earthquake ground motion variable in space? Obviously it is, but in terms of structural response, it's not necessarily detrimental. It's basically beneficial, I would say, and locally critical. The structural system, of course, is the key, because the stiffer a bridge is, the less it can accommodate ground motions. Therefore, very long cable stayed bridges like the Bosporus Bridge, for instance, I would guess, if you like, that is less sensitive to a viaduct that exists and it's let's say, stiffer. Seismically isolated bridges have the benefit to accommodate ground motions, but as long as stoppers are provided, then the response can be quite complicated and they can also experience some increased damage because of this. Deterministic design of new bridges with conventional methods like time history and sports history analysis for special variability, I doubt that it is actually meaningful, because they cannot actually capture the interact excitation of higher modes. Response spectrum analysis can capture it, but because it is special, it is statistically variable, whether it's going to be observed or not, there is no guarantee that it's going to be captured accurately. Therefore, either we have to deal with the problem probabilistically or do something else. And this something else is what I've proposed and I've shown as a Eurocode 8 possible solution, which effectively runs tailored analysis to excited modes, and then these specific amplification factors are applied to specific pairs that are associated with these modes only. And this is a, if you like, we hijack the problem a little bit and we jump directly only to the elements that can be potentially harmed by special variability. For pipelines, clearly there is a problem in geotechnical discontinuities. It's not very often, but it can happen. And because we've got the geological profile, it can be predicted in advance. And for pipes connecting industrial facilities, of course, flexibility will always help for the very same reason I presented for bridges. So with these ideas, I would like to once more thank the organizing committee, the Secretariat, for your kind invitation. And this is just my acknowledgements to my co-authors and collaborators in several projects and papers that I've presented so far. Thank you once more. I guess that we can switch now to myself live to answer questions if any. Thanks again.
Okay, thank you very much, Professor Sextos. This was a very nice presentation, and it was really covering the wide perspective for the structural engineering and also the geotechnical engineering. And if there's any question from the audience, I would like to take it now. I may ask one question, if you don't mind. The spatial variation, it is really just the edge of this geotechnical engineering and also the structural engineering. Because here particularly you gave an example about the large span bridges, and also this is also included in a way the pipelines. And I know that there are some other structures which are really just having the huge large span, for example, the tunnels. So these are affecting from the spatial variation of the ground, and also the waves velocity is different in the medium. So here's my question indeed. Did you have any chance to test that in the dams, the large dams? Because the large dams are something like different from these bridges because they are the continuous structures, and perhaps there is also the spatial variation not over the ground but also through the structure.
This is a very interesting question, indeed. There is a practical issue with respect to bridges, tunnels, dams, and buried infrastructure like pipelines, but we have to make a clear distinction between systems that are supported at distinct points, finite number of points, like a bridge, versus a dam, a pipeline, and a tunnel that are continuously supported. So overall, it seems that structures that are continuously supported are less prone to spatial variability effects because the changes are applied more gradually, if you like. So bridges, large span bridges, represent the extreme case of this phenomenon. However, there are some very interesting papers and work mainly by the group of Professor Chopra on dams that you may refer to. And for pipelines, there is a series of papers that I also listed and we can refer to. The second very important difference is that when we're assessing the response of above ground structures, the intensity measure tends to be spectral acceleration normally because the structure oscillates, whereas for below ground structures, it's going to be permanent ground formation, for instance, or peak ground velocity. So the phenomena are different. But to answer to your question, there are extreme cases for all, but I think the bridges represent the most, let's say, pronounced problem where spatial variability can be critical.
Okay. I think we got the answer now. Any question? Yes, we have one question from the audience. Do we have the microphone? Can we lend the microphone?
Thank you very much. Tassos, this is Eren Uçkan.
Hi.
Impressive presentation. You showed us different examples, especially the one that you showed us about the pipeline is quite interesting because we all know that the wave passage or the elastic waves do not have any harm on pipelines. Well, this is possibly the first or one of the first research that demonstrating that if there's change in the site, that it can be critical for pipelines. Where when you're considering the ground motion for the pipeline, do you consider the longitudinal propagation along the pipeline? What kind of approach? Is it because of a Rayleigh wave or a surface wave? What kind of waves are you considering for that?
In our analysis, we were mainly considering, first of all, we were substructuring the problem into the far field, including the bedrock and a soil profile, which was quite long, of the order of kilometers. And then we were retrieving the ground motion at the base of the trench, substructuring the problem, and then solving locally. So we can assume that we're propagating the waves from the bedrock, which is actually shear waves. Rayleigh waves, I think, and overall body waves, I think most probably they shouldn't be really harmful for the pipe overall, unless, again, there are topographic effects on the discontinuity with multiple reflections, refractions, and superpositions that make things very complicated along the two edges of let's say, a topography of a valley, in a sense. So in every case, ground motions have been produced by assuming these 2D side effects, if you like. Thank you.
Do we have another question from the audience? Well, it seems we don't have more questions, but I think I would like to state one thing. You have mentioned these large-scale examples, large-scale structures for testing. I think in Istanbul, particularly in Istanbul, we have perhaps the largest scale test system because over the Bosphorus Strait, we have 3 suspension bridges. So for example, in the next earthquake, unfortunately, I'm sorry for the Istanbul, but I'm really happy for the Engineering Society because we're going to have a very large and a very efficient data set from these 3 sets of the suspension bridges over the Istanbul Strait.
That is true, but if I may say this, because I've been in Istanbul probably 20 times or so, it's one of my favorite cities, really. I think that, yes, there is an infrastructure that is exposed to the next big earthquake, but at the same time, as Professor Bray very well said, there is great respect in the international community about the degree of knowledge of the Turkish Society for Earthquake Engineering. So most of the newly designed structures, I'm quite confident on the way that they will respond. Obviously, in Turkey, but also in Greece, in Italy, in many countries, the problem is the substandard structures that have not been designed to the modern codes. This is something that real life will reveal what is their actual safety factor. It's not just a Turkish problem; it's an international problem. What we can probably do for the substandard infrastructure. But overall, for the new structures, I'm quite confident that they are designed with the appropriate safety factors, considering, of course, special variability where needed.
But I think with such conferences and with such events, I think we are just increasing the awareness to the earthquake, not from the academic side, but also from the society side also. I think I can just thank Professor Sextos for his presentation. Thank you very much for the presentation. And I think we can just end the close the day for the first day of the conference. Sanırım günün en tatlı anı esasında şu anki an olmuş olacak galiba. Geldiğiniz için çok teşekkür ederiz. Kapanış konuşmasını Ülgen Hocam yapmak ister misin? Yoksa ben devam edeyim mi? Okey, sizleri burada gördüğümüz için çok teşekkür ederiz. Saat 7, uzun bir gün oldu sizler için. Yarın saat 9'da tekrar başlıyor olacağız. Çok teşekkürler efendim geldiğiniz için. Görüşmek üzere.